Oh, no, I mean Singapore. He's also one of the maybe the most prolific Scala open source contributor. He built a whole stack of systems, starting with the popular Ammonite REPL that is actually being merged into the Scala CLI now. The two are essentially feature complete, and I think Ammonite is going to be merged soon. The middle build tool, he will talk about that, and a whole stack of open source libraries from testing to pickling to web servers and so on. So please, how are you?
See if it works. Okay, that works. Let me just set this up. Okay, hi everyone. So my name is Howie, and this presentation is going to be about build tools. So the motivation for this talk is that build tools are kind of the messiest, dirtiest parts of most people's code bases. Like you have your beautiful, pure functional like architecture, you have your object-oriented like a program, and then you have a bunch of bash scripts kind of wiring it together with some Python, with some Ruby, and with some Perl mixed in just for the heck of it. So even with your newer build tools like Scala's SPT or Maven or Gradle in other languages, it tends to become very messy, even though the languages themselves tend to be pretty nice. Like Java is known to be very easy to learn, Maven Gradle is not. Scala is known to be very easy to program, but SPT is not. So this presentation, we'll talk about how some ideas from functional programming and object-oriented programming can really help simplify this build tool problem. We'll talk about why build tools are hard from a user perspective, kind of empirically, why do people have problems using build tools like Maven, Gradle, or SPT. We'll talk about why build tools are hard from an implementer perspective, like why haven't people just gone and made a better build tool and fixed all the user-facing problems. We'll talk about one of my open source projects called Mill. Mill tries to make progress in these areas, and we'll see what it's able to do. And this idea of functional and object-oriented builds, which I think is why my Mill project is able to make progress where other build tools have really struggled in the last 10 or 20 years. So just a bit about myself first. I've been working on open source projects in Scala since about 2012. There's a short list here that's a bit incomplete, but gives you a flavor. The REPL, the build tool, serialization, file system, HTTP, all sorts of libraries. My professional expertise is in developer tools. So I've worked on everything that happens before your code goes to production, whether you're a dev environment VM, your IDE integration, CI system, integration testing system, and lastly, the build systems, which is a topic of this talk. So I'm the author of the book Hands-on Scala Programming. If any of you want to learn Scala, it's a good book. Go read it. So first, let's talk about why build tools are hard from a user perspective. So in Scala, most people use a build tool called SBT. It's an extremely powerful build tool, extremely flexible. It can be very performant if used correctly. And the last thing is kind of the crux of the matter. Like, it's quite hard to use SPT correctly. And often, if you don't use it correctly, the performance kind of is poor, ID support's not great, and the extensibility model can be quite challenging. As Oliver mentioned, we have Scala CLI now. That's a good alternative for small projects, like one file, maybe two files. Once you have 5 files or 10 files, it becomes out of scope. So just the example of the challenges using the SBT build tool in Scala ecosystem. Just running SBT is quite unlike any other command line tool you've used in the world. You don't just run SBT full from the command line because the performance will be poor. So you open up SBT shell, you need to make sure it's run. There's a whole documentation page about managing this shell. And this is all separate from what you actually want to do, which is build your project. Like, I don't want to learn SBT, I want to learn to use my project and just have the build tool get out of the way. Another thing that I hit more recently was I wanted to try parallelizing some tests in one of my projects that I was working on that used SPT. And it took me 2 hours to turn on test parallelization, and I ended up giving up. So you have parallel execution in tests, which is what you normally use. You have concurrent restrictions, which you may also need to set, but you also need test fault parallel, which is separate from parallel execution, which has a separate set of concurrent restrictions. And then you have your test grouping, which may or may not make your test suite slower, depending on the exact kind of runtime characteristic of your test suite. So no one's going to help me with this. I had to get help on Discord after I gave up. But in general, it's a lot more difficult to do things that you'd expect not to be that difficult in SBT. Another area that build tools often fall short is IDE support. I can show you this in SBT, but this actually applies to almost every build tool. Maven, Gradle, Bazel all have the same problem. So if I look at, for example, the Gatling code base, Gatling is an open source load testing framework built on Scala. It's built using SBT. Here it is in the terminal. Can you guys read this code? Yes? Barely? Okay, bigger. So it has 20 submodules. You can see the SBT build files here. There's syntax highlighting. I can jump around a bit. But if you try to jump to the wrong place, like here, let's say you didn't know what library dependencies was, you'll find that there's nothing helpful. I can't find usages. I can see it within my own project, but where does it actually get used within the build system itself? Like, what if I modify this? What happens? How can I find out an IDE? I just cannot. And if it is very different from if you look at the actual Scala or Java code in this code base, let's say I pick some random part of the code. Maybe this is not such a helpful one. Let's look at this one. So like anything here, I expect to be able to jump to definition, even things in the standard other classes, aliases elsewhere, even in the standard library, I expect to be able to jump to definition. So in any Scala, Java, Kotlin, nowadays Python, or Java's TypeScript code base, you expect to be able to navigate around in your IDE, even when the documentation is not there, even when documentation is out of date, even when ChatGPT cannot help you, your IDE is meant to be able to help you find your way around. And you can do this in the Scala code here, but you cannot do this in the Scala code in SBT. Like I jump to SBT spotless and I get nothing. So why is that the case? The basic problem here is that when I look at things like library dependencies, this is really just a global mutable variable. You can see that if any of you use global mutable variables in your application code, you know that jumping to a global mutable variable, you get the type signature, and you get nothing else, right? Because anyone could be setting it, anyone could be reading it globally, and the IDE, just like humans, aren't able to figure out where the data is coming from or where it's going. So just because in SBT we wrap the global mutable variables in this setting key monad interpreter thingy doesn't make them any less global or any less mutable. And that's why IDEs, even though it's the same IDE and the same Scala language, are unable to navigate around SBT code, even though they can navigate very well around the rest of your Scala code base in the same project, in this case, Gatling. So that's IDE support problem. I showed you SBT, but really it's a general problem. You open up Gradle, try to jump to definition, you get stubs. Open up Maven, try to jump to definition, you get XSLT, again, stubs. So even though these build tools all have IDE support, the IDE support is relatively poor. The last thing I'm going to talk about is extensibility model. So every build tool has a bunch of built-in features, hopefully it does what you want. If not, every build tool has plugins, hopefully it does what you want. Again, you often will find things that plugins cannot do or plugins don't quite do the way that you'd like them to do. And every real project has some special stuff. Like your web server, like the Netty code base, may have some C code you need to compile using GCC or Clang. Or some other projects may need to do bytecode mangling or special package formats or so on. So just as a straw man example, let's say I want to count the lines of code in a project and save it in a line count txt file to be used at runtime. Just an example thing that people may want to do. But doing this using SBT is not impossible. Here's an example snippet that I managed to come up with, but surprisingly challenging. Like the thing on the left is that you expect like a new grad to be able to do it in about 30 seconds. The thing on the right will take a lot of fiddling. You may ask Google, you may ask ChatGPT, they may get it wrong, you may fiddle around some more. And in the end, you get something you're not really sure is right or not. And you hope it works, and maybe it does, but maybe it doesn't. Like if I ask any of you, is this correct? Who can give me confidence and say, yes, this is correct? Like, it looks right? Like, but if you look at the business logic or build logic, it is correct. Like the build logic is basically trivial. Docs, single line to count the files, write it to a file. This is correct. But the other stuff that I'm sure most of you would have trouble with, like, do you need def.task here? Do you need the task value here? Should line count be in compiler? Is line count okay to not be in compiler? Should it be in this build? That's very hard to figure out, even if you are an expert with Scala and even if you've used SBT before. And it's not just a problem with SBT. So here's an example Maven implementation. And this one is not correct. And let's give you 30 seconds if anyone can figure out what's wrong with it. So this is uses a Maven XML plugin, exec plugin, configures Maven to run sh-c to count the lines of code using find, pipes it to word count-l, which does a line count rather than a word count, and puts in line count.txt. Okay, so this doesn't work on Windows. Any of you who use Windows here, it's not going to work because Windows doesn't have sh. Any other bugs people can spot? And which is the most simple configuration of one of the most common build tools in the world. We forgot to escape our XML ampersands. We also forgot to escape our caret here, our pipe here. This pipe also needs to be escaped. So yeah, this is a problem. Same thing happens with Gradle. In this case, I have a Gradle build that does the same thing. It's complicated. And again, there's a bug in it. I'm just going to tell you the bug because you guys are not going to spot it. The bug here is we are depending on the wrong set of input files, which would mean that this task would rerun if you touch anything inside source main, even if it's not inside source main Java that we care about. So if you touch source main templates or source main resources or source main config, it'll rerun this task even though the output is the same. And there's no way for you to test this because the output will be correct. It'll just be non-deterministically slower sometimes for a reason that no one in your team or no one in the world will be able to figure out. And so these problems with SBT, Maven, or Gradle, the challenges of configuring the build tool are why people are often so reluctant to do anything with the build tool. You will screw it up. No one will be able to catch in code review. Your plugin authors will screw it up. That's why your plugins sometimes are buggy or sometimes don't work well together. And that's why build tools have a reputation for being so fragile and so hard to work with. So that's the build tool problem from a user perspective. But if build tools are so problematic, why don't people just fix them, make a better build tool, and get on with your life? And the answer is that build tools are quite problematic from a implementer or designer perspective as well, not just from a user perspective. So every build tool starts off simple. For example, this is an example from the JBang project, which lets you run a single file Java application with some dependencies at the top. Just have some magic comments saying that I depend on the library, I depend on this Java version. You run JBang, it'll download the library and run your single file Java code very easily. But most programs are not so simple, and most programs need more configuration. So instead of having a flat list, maybe we'll have like a very big list of configuration values. Maybe you end up putting in some kind of hierarchy to keep things neat. And that's how you end up with something like this GitHub Actions config, where GitHub Actions can be thought of as a build tool / CI system of sorts. You see it's a bit neater than having a huge list, even though it has quite a lot of configuration in it. And it's using a YAML syntax, which is also very common in the build tool. So it's equivalent to JSON, but with a few less curly braces. But if you look at this a bit more closely, it's not really a hierarchy if you look at this config. I'm like defining variables, and I'm passing them into what looks like a function that you can call, and I'm using the variable in the function body. I'm defining a job here, and I'm referencing it here. I'm defining a shared template here, and I'm referencing it in these two other jobs. So although many of these build tool configurations look like a tree structure, it's in YAML, or it's in TOML, or it's in JSON, or it's in XML, in reality, the thing you actually care about is not the tree, but the graph. So that's what makes build tools complicated. Build tools, in general, are really ways to do these templated graph computations. Like for example, in the bottom, you have an example Scala / Java project with 3 modules. Each one has an assembly task, each one has a compile task, but kind of wired together in the graph. They look similar in each module, but not quite the same. So we need a graph because we need some way to order and parallelize the build steps. They need to be computations because class files or jar files or compilers don't invoke themselves. Someone in Bash or Java or Scala or Kotlin needs to specify how these things are created at each step. And needs to be templated because the different modules in the build will often look very, very similar, but are not quite the same. So lots of ways to model this. We saw GitHub Actions had needs keys defining a graph, Bash snippets to define the computation, templating using curly braces. Maven will have its own thing with library dependencies and so on. Some tools try and hide this in plugins, but the problem doesn't go away. If the build tool's hard to work with, the plugins will be buggy because the plugin authors are just humans as well, and they'll have problems working with the build tool. And this results in a lot of challenges making a build tool. So this is a short, incomplete list of questions that the build tool needs to answer that is unrelated to anything that you care about the build tool doing. So ignoring Java, Scala, class files, compilation, ignoring assembly, ignoring dependency management. A build tool also needs custom tasks, CLI syntax, task, kind of data passing between tasks. How do you customize existing tasks because you will want to do that? How do you define task dependencies? Do you use depends-ons like we saw with Gradle earlier? All of these questions are necessary to answer, and if you look at, for example, the Gradle config we saw earlier, the complexity of this Gradle config that's so error-prone basically maps one-to-one with the complexity of the domain of the build tool. So build tools need to do this. Gradle needs to do all this too, and that's why Gradle is complicated. It's not because they want to make it complicated, but in some ways they didn't have a choice if they want to model everything a build tool needs to do. And this is, after that, you have to look at the things that you actually care about the build tool doing, like resolving dependencies, compiling source files, zipping things to make jars, all things which are very side effect heavy, just full of side effects, writing to disk, pulling from network, all things that don't fit well within a normal object-oriented encapsulation or functional programming purity model. So that's why build tools are hard for implementers. Like if I ask any of you to make a templated graph computation API, it'll probably be a very complicated API because templated graph computations full of side effects are inherently very complicated. So next, we'll talk about one of my open source projects, Mill, which is a build tool that tries to make progress in this area. So Mill is an open source build tool. It targets the JVM languages, Scala, Java, Kotlin. There's some experimental Android support. Someone's adding Groovy. It aims to be a lot easier to use and faster than most of the other build tools. It's used quite broadly in the Scala ecosystem, not the majority, but there's a big subset, including Scala CLI that we mentioned earlier, Corsair, the guys doing hardware design with Chisel all use Mill. There's documentation at millbuild.org if anyone wants to check it out. Mill build files are written in Scala, you see on the left. Even if you're not familiar with Scala, hopefully it doesn't look too foreign. There's packages, imports, objects which extend classes, methods. The only thing that you might want to know is methods are defined using DEF if you haven't used Scala before. And it's run using this /mill bootstrap script, similar to /mavenw or /gradlew you might have seen elsewhere. So you can say compile, run, test, assembly, run the assembly later, all the standard build tool things. So the standard build tool things aren't so interesting, but let's talk about how Mill tries to improve upon this in terms of making the performance easier to get, in terms of the ID support, and in terms of the extensibility model. First, performance. In order to compare performance, you need the same project built using multiple build tools. You can't really find that in a while. So just as a proof of concept, I ported the Gatling project from SPT to Mill. Got all the tests passing. It's not a small project, so it took about a day or so to port. But this is quite a realistic port. Like all the flags are set up correctly, dependencies set up correctly, sources, and so on. And what we realized comparing SPT and Mill is that SPT really has two different performance profiles. If you use SPT cold from the command line, which is how you use every other command line tool in the universe, the performance is really poor. And if you use SPT hot by opening this REPL, the performance is actually quite good, but you have this human overhead of managing this stupid little REPL. Like if you Control-C, you need to get back into it. If you change the build config, you need to remember to reload it. All these annoying bookkeeping things that you'd wonder why a computer can't just do it for you. And that's basically what Mill does. So Mill is similar to SPT. Mill does have cold start problems. It runs on a JVM after all, and JVM is known to have cold starts. But Mill manages this background daemon on your behalf. So you always get the performance similar to the hot SPT performance, but you don't need to jump through hoops yourself to get it. You just run Mill something from the command line, and Mill will start the daemon, reload the daemon, restart the daemon as necessary. Like it's not rocket science, but Mill does it and makes working with it just a lot more pleasant and easier. Other areas that Mill tries to improve upon this is large code-based support, so things like supporting multiple languages, things like working with very large numbers of submodules, so even if you have 500 submodules, Mill doesn't get slow, whereas SPT tends to get quite sluggish at that point. Selective testing, where you make a change and Mill will do a breadth-first search in the module graph and only run tests downstream of that code change. So this is very easy to set up in Mill and can really save time and money on pull request validation. It's possible to do it SPT, but usually can be quite tricky and manual to set up. Last thing to mention in terms of performance is the build profiles. So the question everyone asks about their build tool is, why is it taking so long, and are we done yet? And SPT, Mill rather, generates this profile for every command you run. So if I go to, let's say I go to my Gatling code base, and I do a Mill clean and Mill compile all. Sorry, I might make this bigger. So every command you run in mil generates this out/mil chrome profile.json file. So this is a standard format defined by the Chrome team at Google. You can Google Chrome tracing format. And if I open up my Chrome browser, I can go to chrome://tracing. All of you can do this. All of you already have Chrome. So any of you can go to your chrome://tracing UI and get a page where I can dump Chrome profiles in and see exactly where the time is being spent. So in this case, for example, it took about 24 seconds to clean compile the whole Gatling code base. And the question you may ask is, hey, is that good? Is that bad? Am I actually using all my cores? Am I bottlenecked? And of course, you can squint at the terminal and try and see what's happening. But what mil makes it very easy to do is it lets you see just every command you run, where did the time go? I was bottlenecked on Gatling core here. I was well utilizing all my CPUs here. I got bottlenecked on Gatling test here, and so on. And from this, you can take action to improve things without having to be a build tool expert. Even if you know nothing about mil and you know nothing about the Gatling code base, hopefully you could have some ideas of this, of what you can do to improve the build time if you wanted to do so. Like maybe I can break up Gatling core to parallelize it, or break up Gatling common to parallelize it, so you can run in multiple smaller submodules that can compile in parallel. So that's a performance angle. I think it's pretty neat. It's just easier to get performance. Nothing I showed you is impossible with SBT, Maven, or Gradle, but they're difficult enough, you probably won't do it. You probably won't set up selective testing. You probably won't set up build profiles. So you kind of just suffer with a build tool that's slow and flaky and you don't know why. Whereas mil makes it easy enough that you can easily figure out what's going on so you can get the best performance out of your build tool without too much effort. Next area I'm going to talk about is the IDE support. Mil has better IDE support than any other build tool. And let me show you what I mean by that. So let me pull this up. So core. So over here on the right, I have the mil build config for the Gatling core submodule. And on the left, I have the SBT build config for the Gatling core submodule, one of the submodules within the Gatling project. So the first thing you might realize is that although they're spelled a bit differently, like one uses lazy val, one uses object, one uses equals, one uses extends, they really have the same information. Like core depends on netutil, depends on quicklens, depends on common, also as a test dependency, depends on JSON path, also as a test dependency, and so on. So this module requires this configuration to set up, and mil is no exception. We need to pass it in. Where mil is different is that while SBT configures things using these global mutable variables where you jump to them and there's not much there, mil configures things using method definitions and overrides. So for example, let's say I override this key fork args equals, I don't know. And let's say I didn't know what this is, right? Maybe I'm new to the project, maybe something's misbehaving, I need to figure it out, maybe it comes from a plugin that's not well documented. How do I figure this out in mil in the IDE? Well, like any method, I can ask for its type signature and name. You can see here it says sequence of strings. I can also get its documentation. You can see here any command line arguments into pass to fork JVM. But let's say I want to learn more than that, like if something's going wrong. I can also see that this is an override. IntelliJ also knows that this is an override. I can jump to the overridden method. I can see the value that was there before I overrode it. This is something I did not get in SBT. I can see it was previously an empty sequence in this case. And I can also find usages in my IDE and see everywhere in the build system that uses this kind of configuration. So I'm setting fork args, but I don't care about setting fork args. I want fork args to do something else, and I want to see what fork args is doing. In SBT or most build tools, it's basically impossible. You go to like library dependencies here, and there's nothing. Whereas here, I can see that, well, if I search for fork args gets used in runner gets used in run background task, and run fork task gets used in run. So just like that, I can navigate around the build pipeline, just like I can navigate around any Java, Scala, Kotlin application code. And if something's misbehaving, I can figure out what step it's happening at and what's going on and what may be going wrong. I show you navigating downstream. I can navigate upstream as well. Like for example, let's say I look at this final main class thing here. No documentation. There's a type signature, but no docs. I jump to it, again, no docs. In most build tools, you'd be totally stuck here. Ask ChatGPT maybe. Here, at least I have the implementation, and I can see that this basically delegates this final main class opt thing. And let's say there's no docs for that either, which there isn't. Again, in Mill, you're not stuck because even though the name may not be too clear and there's no documentation, I can see what the implementation does. For example, it delegates to main class. This says any explicitly specified main classes defaults to none. If there's one, I use it. If there's none, I call all local main classes. All main classes detected. So this one uses this class graph project to look at your class files and search for public static void main methods that look like main classes. If it detects an empty sequence, it reports an error. If it finds exactly one main class, it uses that. If it detects multiple, it reports like another error, saying that, oh, we found multiple main classes, please tell me which one you want to use. So what's interesting here is that this is the experience that you get day in and day out in all your application code. In your application code, you never have good enough documentation. Application code is all proprietary, it's not on Google or ChatGPT. But nevertheless, because you have an IDE and because it's a strongly typed language, you can navigate around your application and figure things out even when things go wrong, even when things are not perfect. Whereas in most build systems, you basically have copy-pasting things and praying things go well, because when things go wrong in most build systems, there's no tools for you to help figure it out. Well, Mill brings application code experience to your build tool, so that in Mill, if you're not sure what something's doing, you just navigate around your IDE, upstream, downstream, up and down the dependency graph or call graph, just like you would in your application, so you never get stuck. You can always figure out what's going on. That's IDE support angle. Last thing we're going to talk about is the extensibility angle. So I think what's interesting here is that where most build tools require extensions to be published as plugins, Mill lets you just write code and import libraries to use in your build directly. And what does this mean? Let me show you. So over here on the right, I have the minimal Scala build using Mill. So it uses Scala, in this case 213, in the foo submodule. It's a Scala module, and that's all. So I can do like mill, ./mill foo.compile, for example, and it will compile my build, my project. But let's say I didn't want the defaults. Let's say I wanted to do something special. Like let's say I wanted to count the lines of code in this project and add it as a line count txt file. So in Mill, tasks are just methods, and every custom task is just a method you define. So I can define a method called line count, which is a task. I can call other methods within it. For example, I want to call all sources or all source files. If you're not sure, again, you can ask your IDE. The IDE will help you along. And I can map it to, for example, file.path, os.read.lines.size.sum. So that's all I need to do to define a custom task in Mill. It's just a method that's wrapped in this task block, calls other methods, and returns a value. I can now do mill show foo.line_count. It might take a moment to compile the build again. 17 lines. I can do mill inspect foo.line_count. You can see we automatically capture the Scala doc for you, automatically capture the line number, file name for you, all that stuff. So this is my custom task in Mill. Very easy for you to write, if any of you know how to write code. But we haven't wired it into our resources yet. So in Mill, resources, again, are just tasks. Tasks are just methods. And the way you customize a method in any object-oriented program is by overriding it. So I can override def resources. Again, you're not sure which one to override. You can ask your IDE. I can say, well, I want to keep the super resources so I don't throw away my resource folder. But I also want to write to my task.destination folder, which I'll explain in a moment, my line count as a string. And I'll append this reference to this to my resource path. So let me show you this, mill show foo.resources. So you may ask, what is this task.destination folder? So the task.destination folder is important because in any build tool, the world's biggest global mutable variable is a file system. Everyone's just reading or writing all over your file system. You don't know who's reading or writing to where. If you parallelize it, they may stomp over each other. If you delete something wrong, you don't know who's going to be affected. You can't easily clean your caches because of that. And that's why you end up with things like in Maven, you call Maven clean installed on every command you run because you don't know what's going to run on what order. So in Mill, the way you work around this problem is instead of a global mutable file system, every task gets this resources.dest folder. In this case, output/foo/resource.dest corresponds to task.dest here. And this is a locally mutable file system within the task that is globally read-only. So rather than a global mutable file system, you end up with some local encapsulated mutability, but that's pure with regard to other tasks trying to use it. And that makes things much easier for the build tool and humans to reason about it. So now if I look at my out slash foo slash resources.dest, I can see my line count txt file, and I do mil foo.run. I can see my application is able to pick it up, and in this case, it's printed out at runtime. So let's take this one step further. Let's say I want to use a third-party library. Again, a common use case, just as an artificial requirement, let's say I want to render my line count as HTML. So mil doesn't have HTML rendering libraries built in. So if I try and do this from the command line, you'll see it yells at me saying, hey, I don't have this Scala tags library to render HTML. What mil does let you do is it lets you very easily import these libraries in the build header. So I can say commonly how we Scala tags, I need 2 colons here, 0.12.0. Now, if I reload this, and if IntelliJ is feeling happy today, IntelliJ is not feeling happy, so I have to reload my IntelliJ. Let me do that in a moment. And reload this here. Okay, so now that I've reloaded this, I now have my Scala tags library just included as part of my build. So I can, for example, I can write another task. Def HTML snippet is a task that I call a div h1 line count, paragraph line count as a string, dot render. I can call this instead of my line count when I generate my resources. And now when I do foo.run, you can see that it's now generating HTML at build time using a third-party library along with some custom logic. This HTML is cached on disk. I can look at my out slash foo slash HTML snippet.json to see the HTML cached on disk together with some metadata that mil uses for validation. And what's most interesting here is that when you look at this build config, it's basically a very boring object-oriented program. You have object foo extend Scala module. You have a bunch of methods calling each other. You have a third-party library, just a normal Scala tags HTML library. What you don't see is you don't see like special build tool APIs or plugin APIs. You don't see special like HTML rendering plugin or text rendering plugin or resource generation plugin. Because in mil, even though there are plugins for many common tasks, if you want to do something special, you can just do the thing rather than trying to find some plugin on GitHub last updated 5 years ago that maybe does the thing for you but in a half-broken way. So that's the programmability angle. Earlier we saw how hard it is to detect any bug in your SBT, Gradle, or Maven config. But hopefully you can see in the mil build, it's a lot clearer what this thing is doing, and hopefully it's a lot more obvious when it's correct, and also it'll be a lot more obvious if something goes wrong. You'll be able to catch it in code review or in testing. So that's this demo we saw live. Okay, so that's the user-facing improvements that mil provides over SBT and other build tools. But the obvious question then is, well, why doesn't everyone else have this? Like, Maven's been trying to improve these things for 20 years. SBT's been doing this for 15 years. Why haven't they managed to improve it? And I think what's been missing is this idea of functional and object-oriented builds that really underlies all these mil features and user experience. First, this idea of build graphs as pure functional programs. Basically, everything a build tool does, 99% of it, is do things to inputs to make outputs. There will be some weird edge cases where you have to mutate your inputs, like if you're reformatting your source code, okay, you have to mutate the inputs. But most of the build tools, actions, you don't touch the inputs. You only make a new output that is separate. And if you look at the things we saw earlier, all these seemingly side-effecting I/O-heavy actions, downloading from network, code generating, reading, writing to disk, all of which can basically be thought of as pure functions. And yes, you have to read and write to disk, but as I mentioned earlier, you can kind of treat the disk as pure if you encapsulate the mutability, so only I can write to my folder, and you guys can only read from it. And from your perspective, you can basically treat it as a pure functional disk. I get this file from someone upstream, and it's a read-only file, it's immutable value, and I can't touch it in any other way. And all of these actions you see here, assembly jars, class files, test results, all fit into this mold. And what's interesting about these pure functional programs, pure functional build steps, is that once you get rid of this global state, global file system, you end up having these tasks that only read their inputs, only return their outputs. Both of these can be files on disk. But once they're functional, they can be parallelized, cached, and scheduled very easily both by humans, but also by the tool. So the tool can say, hey, you three run in parallel. I know you're not going to stomp over each other's files on disk because you all have separate folders to write to. I know you're not going to mangle other people's files and have race conditions because all other folders are read-only to you. So Mill can do this because these tasks are pure functional, and therefore can do this on your behalf without you having to deal with executors or locks or scheduling yourself as a build tool user. And pure functional programming, again, is what makes jump to definition in IDEs useful. If you have a global mutable variable, like in this case in SBT, you jump to it, you get the global mutable variable's type signature, maybe it's docs comment and nothing else. Whereas if you have pure functional tasks, I have all source files, I don't know what it is, I jump to it. I don't know what's all sources, I jump to it. I don't know what sources, I jump to it. I don't know what's find source files, I jump to it. In a pure functional program, every jump to definition is useful. And that's what part of what allows Mill to have so much more rich and IDE experience than we saw earlier with SBT, or you would see in other build tools like Maven, Gradle, or Bazel. So that's build graphs as pure functional programs. Like people often think build tools are these sketchy things full of side effects and bash scripts, but with not too many changes, you just put your side effects within a nice encapsulated folder and treat it as read-only from everyone else. You can really treat your build tool as a pure function, as a bunch of pure functions with all the benefits that entails in reasonability, scheduling, and other things, parallelizability. The other thing I'm going to talk about here is the idea of object-oriented build definitions, which I also think is very unique in the Mill build tool. So earlier on, we talked about this idea of templated graph computations, how every build tool needs to do it, whether you're writing XML in Maven or Groovy in Gradle or pseudo Python in Bazel or just bash scripts. And pure templated graph computations are complicated, so if any of you try and come up with a templated graph computation API, it'll be a very complicated API. So what do you do about it? Well, it turns out that everyone here already has this way they've been writing templated graph computations for the last 10 or even 20, 30 years. And that's called object-oriented programming. So object-oriented programming with objects, classes, methods, overrides, super, and other method calls are exactly a fit for a templated graph. And if you look at what this means, if I say object foo extends Java module, it's an object that extends a class. You all know what objects extending classes get. They get their methods, and the methods call each other. And if I add a new method, line count, that calls all source files, or I override a method, resources, that calls super and also calls line count, I don't need to teach you anything at all for you to know how this will affect the graph on the top right. You know how object-oriented programming works. You know how override and super works. You know that this stuff gets spliced in. You know assembly calls the new resources, that resources call the old resources, that call super. All of that you already understand without me having to teach you a single thing. And if I want to template the graph, I just take my object foo, which was a singleton, I turn it into a class or a trait in Scala, and I extend it twice in two different objects. Ta-da, I have templated my graph. And you can do other further things as you'd expect. I can have further customization in each of these objects. I can have subclasses, I have customization shared between objects. All your standard object-oriented techniques for managing your code running in these method calls and classes perfectly fits the common things you want to do when you're templating a build graph. And once you have the build graph, you can do things, Mill can do things like, oh, look at compile and line count don't depend on each other, and because we saw earlier that we can treat them as pure, we can run them in parallel. Every method has a name fully qualified, like foo.linecount, foo.compile, foo.assembly. So we can use a name from the command line without you having to have a separate method task name. We can also use a name to assign every task a unique place on disk to put its JSON metadata and its .destination folder for file outputs. And these are guaranteed to never collide, so that we can treat them as pure and kind of encapsulate the mutability within each individual task. And we can do incremental invalidation. For example, if we touch a resource folder, which is now called super because we overrode it, Mill can just do a breadth first search, see assembly needs to recompute, see compile and line count do not need to recompute. Mill knows where to get the old output for compile and line count because it's here on disk at a standard location, so you can reuse it. Mill knows where to find the old output for assembly, again at the standard location, so Mill can delete it and recompute a new assembly from scratch. And what's most interesting here is that in this case, you see there's no code on the left related to any of these things at all. What you have here is a very boring object-oriented program with object extends class, method calls method, override super, all concepts that you probably learned in your first year of college or programming class in high school. What you do not see is you don't see depends on clauses, input, output, file registration clause statements. You don't see threads or mutexes or locks or semaphores or other concurrency-related things. You don't see cache key computation, cache invalidation. So Mill's able to squeeze all your user-facing code into an object-oriented model that's actually very simple for people to understand, and handle all the build tool-related stuff largely behind the scenes. And earlier, we saw this long list of things that, for example, Gradle needs to do, and how it corresponds to things that the build tool requires. Mill also needs to do all these things, but Mill squeezes it all into this object-oriented facade. Like, how do you define a custom task? Do I need to use a task.register callback with a string with the task name and the lambda block saying the body of the task that does side effects? No, I just define a method. What's a task output? Do I need to write it to some output somewhere and register it somewhere? No, I just return the value as a return value of the task. So all of these things Mill does handle, but it handles in a way that's much more familiar to anyone who's learned Java 101 or Python 101 like 10 years ago in school. So just to wrap this up, like the idea of object-oriented builds, your builds are just methods, objects, classes, extends, overrides, super. Everything works as you expect. Everything works as IntelliJ expects and VS Code expects. That's why the IDE support works so well just now. There is no Mill IntelliJ plugin. IntelliJ already understands how all this stuff works. Mill handles all the other things for you 99% of the time, which means you get good performance because you don't have people forgetting to cache things in their plugins. You don't need to clean because you don't have people screwing up the cache key computation in their plugins. You have more time left over to do other things like implementing build tool features, tooling integrations, or working your own application code. And in terms of tooling, talking about tooling integrations, we went and integrated quite a long list of tools for you in case you want to use them out of the box. But if there's some tools you want to use that are not on this list, hopefully it's not too difficult for you to integrate yourself, like what we saw earlier with the line count HTML plugin. So this is the last slide. And I think to sum up, if any of you who are curious about build tools or curious about how functional programming and object-oriented programming in Scala can be used for like a real-world use case, I think you should take a look at Mill and give it a try. Like, Mill not only has some very interesting ideas, this idea of functional object-oriented builds, which I think is quite unique within the build tool ecosystem, even outside of Scala. These ideas aren't just theoretical. They correspond to real-world improvements in things like performance, in things like improved IDE support, and in things like having an easier programmability model. So I think I have 1 more minute. So the docs are here. This is a Mill-build website. We have getting started docs for Java, Scala, Kotlin. We have migration tooling and migration docs if you want to migrate. And if you want to take an existing code base, for example, if I go to if I go to the Gatling code base, I can just like curl down the Mill script and do Mill init, and it will do a best effort auto migration of the SBT build to Mill for you. So you can then, after that, you can run Mill compile, Mill test, and then it'll work. So I think that's the end of this presentation. Thank you for listening. We haven't tried, but we are trying. Yeah, so it hopefully might happen someday. Any other questions?
Yes, I have one. How will you convince people to switch over? I think one part of the story must be converting existing builds in the systems to your thing.
Yes.
Any ideas about that?
So yeah, I showed you just now. So earlier I ran ./mill init from the Gatling code base, which is here. I can now run mill under wildcard.test, and you can see we'll compile and run almost all the tests in the Gatling code base out of the box. There's a few tests that in SBT they have special customizations that Mill's unable to automatically convert, but the vast majority of tests that just rely on compiling code and running it, and with dependencies, Mill's able to run out of the box as you see on the left. So yeah. So hopefully that will smooth the migration path, although it's never easy to migrate, but it'll hopefully make it less challenging. Yeah.
Okay.
Another question. So you said you don't need to handle dependency tracking, parallelization, it does everything for you. So how does it do it? So, because you just write an object-oriented model.
Sure. So where's my slides? So basically, when you see like def resources equals def line count calls all source files, this is kind of like an async await transform similar to SBT or similar to like idiom brackets you see in like other languages, where we turn this task into an applicative data structure, and then the applicative data structure then you can inspect the data structure without first running it. So you can inspect it, schedule it, and then run it in whatever order you like. This works 99% of the time. Sometimes you have to customize it yourself. Like, for example, you may want to have some special cache and validation logic to handle the Scala incremental compiler or the Kotlin incremental compiler. That wants to manage its own caches and isn't happy if you wipe out the cache every time you run it. So in that case, Mill does have some special like escape hatches to go under the hood. But most of the time, you can kind of just close your eyes and pretend it's like a pure object-oriented program. It mostly just works. Yeah.
Okay, let's thank the speaker again. Now it is my pleasure to introduce Edward Lee. And Edward Lee just graduated, and he has a professorship, teaching professorship in Toronto. So congratulate him, please.
Thanks, Oliver.
Great job.
I'm happy to say that I've defended my thesis this year, so that's great.
Excellent. And he's going to tell us how to use mutation without mutation.
Thank you. Yeah, all right. So let me just open my slides and do the difficult part of this talk, which is to get Linux to project something correctly, which is extra difficult because my trackpad loves to misbehave. So there's an HDMI port on this thing. It's on the other side. Will this work? Well, all right. So now we have to do the hard part, which is to mirror the display. All right. Press apply. Keep the changes. Open up your slide deck. Put it into presentation mode. Oh. And then start your talk. So my talk today is going to be about taking away mutation with a fairly catchy subtitle. It is joint work with James, Dimi, and Andre. James is Andre's former master's student. Dimi is now a professor at HISO Valley, if I pronounced that correctly. And Andre is my advisor who's still at Waterloo. And you know, it's nice to see pictures of who you've worked for. So those are those pictures. So why am I going to talk about taking away mutation? Well, mutation is often bad because it's hard to reason about code that has it. If you're writing a build system, as you just said, well, everything touches, you have this global mutable key, value store, and everything touches it, so it's hard to reason about what your build actually does. But sometimes it's actually also necessary. So here's an algorithm. It computes, probably based on the name of this algorithm, the set of prime numbers out of a list. Now, this is what some might call the sieve of Aristotles, but it's actually not. It still computes primes, but it does so inefficiently. And the reason for this is because it filters out primes. It doesn't take away the primes as you see them. It more mirrors what you might do by casting out primes. This is what the real sieve of Aristotles looks like. And you might notice that this is actually a mutable algorithm. It has many cases of mutation. It initializes a mutable array. It uses two mutable counters. And it uses this to efficiently cast away things that are composite as it sees them. It immediately discards composite numbers when they're shown to be composite, unlike the other case where, numbers are like 4 float around for a bit until you filter them out by 2. It relies on mutation, and it's really an integral part of this algorithm. You could, of course, use tail recursion and duplicating arrays to implement this functionally, but it'd be a lot messier. But this kind of also contrasts with our intuition as people who like functional programs of, well, is mutation bad? We'd like to think it's bad, but this is a use case where it's pretty good. And the answer to that, I guess, is like most things in life, there's a lot more nuance than what's on the cover. Since mutation isn't so bad in this case, because it's really just local to this function, real primes. It doesn't escape out of it. All the variables that are mutated are within it. So relative to the rest of your program, it still appears referentially transparent or pure. And this is how state's done in Haskell. RunST and friends use this idea with the state monad to implement what might be an imperative code in Haskell, and you can actually formally show that this is safe with some really cool work that Amin Timonish did in 2018. But that's great and all if your data structures and your variables that are mutable don't escape, but sometimes you do want them to escape. Sometimes you might want to just, instead of returning a list of primes, you might want to return a table of numbers that are true if they're prime and false if they're not. And here, you naturally just want to return the array you generate. Or if you're doing something like returning cyclic structures. You want to return the cyclic structure, but it's really hard to construct cyclic structures without mutation unless you're really well-versed in how, with laziness, and so you kind of want to have the ability to generate mutable structures that escape, but still have these nice safety properties that we just talked about. What you want, or what I say you want, is you want a mechanism for making data mutable only when you need it. And so this is what this talk is going to focus about, is how can you do so with the mechanisms in Scala that already exist to do so. So we're going to use capabilities to control setters, and I'm going to show you how this works. We're going to use singleton types to couple capabilities with our objects so it's safe, and contextual functions to make this all automatic so you don't have to write really messy code. So let's start. We're going to turn this implementation of real primes into something that's, I claim, safe, which is this, which looks exactly like what you would have written originally. So let's do this. So what's the simplest mutable structure? Okay. Come on, someone knows the answer. You look like you know the answer. It's a ref cell, right? So here's the simplest mutable structure. It's a reference cell. It has two methods, get and set. Get returns a cell value, and set lets you set it. Now, if you want to control mutation in the structure, you want to restrict how and when and where you can call set, right? And the easiest way to put additional constraints on when a function or a method can be called is just to require more arguments to it. So here we can modify set, so it takes a second argument k called key, which you might think is, well, named that way for a reason, so that set's only called when a key is passed to it. Now, this is on our way to building something safe, but is this code right now safe? For some intuitive notion of safe. It's not, because I can counterfeit my keys and just pass them around willy-nilly, right? It's like if you had a car, if every car had the same set of keys, right, then you can just steal your friend's nicer car. So there's a hole. So how do we fix this hole? Well, like car keys, which are tied to their cars, we want to really tie the keys that we generate to the capability, to the object that they're associated with. And we can do so with singleton types. I can create two keys. I can allocate two cells that are tied to those keys uniquely by exploiting singleton types. So here, B1 is associated to K1 by tying B1 to say, well, set can only be called with an object of K1.type, and B2 is tied to K2 by, well, saying that set can only be called on K2.type, and then I can't counterfeit my keys. And that's good. Now, there's a bit of a flaw to this approach, which is that cell TK is kind of awkward because it's part of its public signature. Unlike, I can't really reuse this code in the setting where I had cell and T before because, well, now I've got this second type parameter. So how do we fix that? Well, Scala has support for type members. So I can just hide the capability type in the cell, making it not part of its type signature, and exploit that to have nice backward compatibility with code that reads from cells but perhaps doesn't write to it. So code like print cell, which just prints the value in a cell, it can just call c.get without worrying about what key it has. But you can't write functions like write that just write to any cell because it doesn't have the appropriate refinement or it doesn't have the appropriate knowledge of what key opens that cell. And we can also get some nice lexical-ish like scoping. So if I have a function that, makes a cell and mutates that cell within it, I can allocate a key that's hidden in that function, create that cell that's tied to that key by using the appropriate refinement. Here, type k equals k.type. Set to it when I forgot to pass in k, but that's done. And then return it. And since the key isn't escaped out of makesum, then I know that the result can't be mutated outside of makesum as well too. And I can do this automatically with some Scala support for funcs and blocks by having a helper function that just calls a func with the appropriate new key. So I can turn that into something that looks like this. I can write a immutable cell that's constructed mutably, that takes in the key that's allocated to within the scope of transiently, and set it, mutate it, when I'm done return it, and then, or it's immutable outside. And if you didn't like how key had to be passed in, because now set has this third argument, you can use Scala's contextual functions, so it appropriately selects the appropriate key out of the environment, and you can, if you didn't like how I constructed my keys by refinements, I can write a companion object that helps construct those keys with whatever ambient key is in scope at that time. So I can write code that looks like this. I create a box, a cell, I write to it, I return it, and outside of it, I can't mutate it. And that's great, right? And it looks like the code you would have written before. It looks like the code you would have written in the first place with just mutation directly. I can do one more tweak. I can just turn cell. I can turn get and set into the real getters and setters in Scala. And with that, I can just write, well, what looks like pure imperative Scala code, except with transiently to make it all look safe, and is safe-ish. And that's nice. And we can also take these ideas and implement them as a little bit of syntactic sugar in the Scala compiler, which is currently working on 3.5, and I have to rebase for 3.8, so that you can just use an extra keyword, and it'll all do this automatically for you. So what is this good for? Well, we did a few case studies, and I think one really cool case study is, well, here's an example of a pretty class you might have used in the Scala standard library. It's the constructor for a list cell, and we like to think it's immutable, but as a type signature indicates, as a constructor signature indicates, it's not, because next is mutable. And well, why is next mutable? Well, because we like efficiency, and we want our programs to not blow up our stack. So a lot of algorithms in the Scala standard library that operate on lists do so imperatively with imperative algorithms to avoid non-tail recursion. So here's how map's implemented. It applies a function by creating a new list iteratively and adding to that list's tail at each step. Now, the nice thing about what we just did is we can actually just take what we did in your code for list, throw in these ideas for passing around this capability attached to your case class, to the case class, and turn all these functions that work on list imperatively and show that they don't actually leak immutable lists with these capabilities that we've shown that don't escape out of the block transiently. And that's kind of cool, I think. And we can do the same thing for list buffer, which again creates lists imperatively and we can take these ideas, tie the list that the list buffer creates to a capability that doesn't escape the list buffer but is owned by it, and turn the code that imperatively deals with lists into code that safely deals with lists in the list buffer in a way that you can reason and say that the lists that the list buffer returns are immutable while letting them stay mutable within the context of the list buffer. So I think that's really cool. So what's next for us? Well, there's some cool work done by Martin and his team on capture tracking for scoping, which are capabilities right now. You can escape them if you want, ruining your safety guarantees. So it'd be nice to see how capture tracking can be used to help this, to help these ideas along by guaranteeing that these capabilities don't escape when you want, where you don't mean them to. And on that note, there's some cool work by the capture team on actually handling mutation natively within the framework, which I think Oliver and Oliver and friends will be talking about sometime this week. So that's really cool. But I think there's still value for techniques like this, for lighter weight techniques, and it'd be interesting to see how they compare in real usage. And on that note, it'd be nice to see how we can integrate this into other production Scala software. And if you have any ideas, I'm all ears too. So anyways, with that said, thank you for your time. And if you have any questions, I'd love to hear them.
Great talk. Questions?
So thank you for the talk.
Thanks, Martin.
That's very interesting. So you said you can retrofit list and list buffer, which is quite impressive.
Yeah, so we retrofitted list and list buffer in the standard library, and the standard library just compiled.
Okay.
It was actually
So it's proven to be safe. Yeah.
well, it's proven to be safe. Well, you need some. Well, there's a catch there because the capabilities could escape, and we haven't integrated capture tracking to make sure they don't escape. But that's an easy fix once I rebase the library the code to 3.8.
Okay. So my question is, don't you introduce an overhead by passing these implicit parameters?
So yes, so I didn't talk about it in this talk, and there is an overhead if you implement this naively by, allocating these key objects, right?
Exactly.
But there's some cool stuff in the Scala library that allows you to pretend create objects with using erased. And the natural optimization here, which we think will work, but there's been a few bugs in the Scala compiler, either on my part or on the Scala compiler. So we haven't implemented erased to make the capability or the implicits go away at runtime, but we think it's not too hard to actually stick erased there.
So erased recently got a major upgrade, and Eugene is going to talk about that later in the workshop.
Okay, that'd be great. I should talk to Eugene. Thanks for that, Martin.
Any more questions?
So, thanks for the talk. This is really interesting. You don't have to answer this. I know this is an annoying question, but at some point I was reading the Scala library's list buffer source code.
Yes.
And they have these funny memory fences in there. Does this address that in any way? Because you seem to have more semantics now, and they just seem to know they are there.
So no, when I applied this to the list buffer library, I left the fences alone because I don't know the implementation that well too. You may be able to remove it, but this is really just a safeguard for the developer, for people who write the library, so they can ensure that these lists aren't mutated where you don't expect them to, and for the end user, because they can safely know that since no one has the capability, that these lists aren't being mutated in weird ways.
Cool, thank you. That makes total sense.
Thanks for the question, Ivan.
Any more questions?
Thank you for the very interesting talk. My question is, have you thought of extending this to safe concurrency?
So the answer is no, but if you have any ideas, I'd love to hear them about this. I haven't thought, we're still kind of working out the design and where it can be applied, and because we're still looking at, the one hard thing in practice is finding Scala programs that use mutation. That's actually fairly difficult to find. So, but if you have any ideas, I'd love to hear them.
I guess a follow-up is, were you in any way inspired by Rust and like what Rust does with, this scope-based analysis?
I think we were, because we liked how Rust kind of lexically delimits scope by lifetimes and by borrowing and ownership, but we wanted to take an orthogonal note on that because we didn't, we wanted something that was a little bit more, I guess, flexible by using capabilities instead of by enforcing ownership with a linear type system. I hope that answers the question.
Okay, there's one more question.
Hi, Edward. Thanks for the talk.
Thank you for the question.
Yeah, so I was wondering, so why, I'm sure you have a good reason for this, but I was just wondering why the scoping for the key instead of creating the key when you create the class?
Why the scoping for key? So I guess with transiently here?
Yes, yes. So usually what I would imagine is that when you create a stabilizing class as you designed it, you get a key, and now if you have two maps, you have two different keys, and so you don't mess.
Right. Okay, so why do we have, okay, so I think this is partially because of backwards compatibility, and also because we wanted people, we wanted you to be a bit more flexible. We wanted so that you could have, you don't want to, like, I guess the annoying thing with having a single key for each object is that now you need to have a key chain of objects, of keys, right? So for simplicity, this design allows you to associate one key with multiple objects too.
Thank you.
Thank you.
Okay, thanks for the great talk. I think there are no further questions. So before we go to lunch, I have a remark. Here's a gift for you.
Oh, wow. Thank you.
Because you didn't get the t-shirt.
That's my fault for forgetting.
Yes. In the back of the room, you see these boxes, one of the, like this one here. And those are mugs with the Scala logo and Martin's signature. And they're up for grabs. And I'd like to ask you, if you were earlier at Scala Days and grabbed one of those there, then please leave it to others. So because we have a very tiny amount of them left, and you're welcome to take them. Otherwise, I leave you to the lunch. Thank you. He's one of our industrial speakers. Let's give him a warm welcome.
So, does this work? Okay, awesome. Okay, thank you. Hello, my name is Adam Warski. I come from Warsaw, Poland, so far away as well. I'm not from academia. My last contact with the university was 18 years ago when I graduated. But I'm still following, all the developments in Scala and partly in functional programming. So it's my second academic conference. It's quite interesting so far. So yes, I would like to try to answer the question how function is direct style Scala and direct style in general. Like we used to program in direct style a long time ago, but then mainly for performance reasons we moved to a more monadic style using futures, IOs, and so on. But now we have some new features in our runtimes and in our languages which actually allow us to go back to direct style. So are we still doing functional programming or not? I would like to start with trying to answer the question, what's functional programming? So this might be like an obvious thing in this conference, or maybe it's quite the opposite. Maybe it's not so obvious at all because it's the functional programming conference. I talked to some people at lunch and they told me it's not an easy question. So yeah, I will try to answer that from like a practical perspective because day to day, like I'm a software engineer. So then we will try to address the question that's here. And finally, I would like to take a look at some purely functional effect systems, whether we can get some of their benefits in our direct style approach. So let's start about what functional programming is in general. So if you go to Wikipedia, we can read that FP is a paradigm where you construct programs mainly by applying and composing functions, right? And that's a fine definition, I guess. But it's also quite vague, right? Because functions, you use functions in all kinds of languages, right? You do C, you define functions all the time. So what does it really mean to do FP? And I propose that we take quite like a pragmatic approach. If you probably go out and ask some people who do FP day to day, like in Scala, for example, but not only, you can do FP now in Java, Kotlin, Ruby, and so on as well. I guess most of the time you would get answers like, we are using high order functions, you are using immutable data, you are using function composition, you are using functions as first-class values. Of course, your language needs to support lightweight syntax so that it's feasible and so on. So they would enumerate all these tools and techniques that you use to actually do FP. That's opposed to, using explicit loops, having mutable data, combining data and behavior like in the object-oriented style, and so on. So that would be like the non-functional style. I guess the functional programming, as I would define it, is mostly when you are using actually these techniques on the left. But there's also, I guess, two flavors of FP really, and it all boils down to the answer for the question, what's actually a function, right? One way of viewing a function, like the software engineering way, would be that it's like a callable unit of software which has a well-defined interface. You can call it multiple times. But then there's the mathematical definition, right? That for each item from the domain, you assign exactly one item from the codomain, and the function is idempotent and effect-free and so on. So when you are talking about functional programming, which of these definitions do you take? And I guess you can actually take both, right? And I would call the first one casual functional programming. That's like a term I invented. And the second would be pure functional programming, right? And I would argue that there's actually a lot of value in the casual variant itself that actually warrants calling it as separate paradigm, and that is actually very useful. And if we take a look at the degree to which we use functional programming as a kind of a spectrum, you might start with like spaghetti code on the left, so like, just a bunch of imperative code, and then when you try to improve it, maybe you read a book by Uncle Bob on clean code, so we extract some small methods, right? So we will have the functions already. But I don't think you are doing functional programming yet, right? It's when you apply all these techniques that we talk about, like high order functions using ADTs, using expression orientation and so on, that's when you transform to casual FP, and that's where you get a lot of the benefits from FP. Now, you might go all the way to pure functional programming and get the additional benefits like referential transparency, but quite often you would only get diminishing returns. And to demonstrate a bit, here's like 3 snippets of code. So on the left, you would have the spaghetti code version, right? So if you read the code on the left, you don't really understand what it does. But all 3 pieces of code actually implement the same thing. Now, if we move to casual FP in the middle, right, you can see that there's an array of IDs, and then you fetch them from the database, then you do some HTTP, and then you partition it, right? It's much easier to understand than the thing on the left. And it's using, higher order functions, function composition, so some of the techniques that we talked about. And I think the middle version is much clearer than the left one, right? But we didn't go all the way to being pure because we have side effects in our functions. Now we can go the extra step, but we probably don't gain as much. So yeah, so that's how I would define FP by actually more of the practices that you use in your programs than anything that you can, that's very, that has like a very clear definition. So if you are using some of these techniques that are listed here, or maybe most of them, then you're actually doing FP. And I think the distinction between the casual and pure variant actually also might have a reflection in history. So that's one answer from Stack Overflow. Like, I'm not very good in history of programming languages, so maybe that's wrong because the internet is wrong sometimes. But it says here that the original definition of FP came from FP originally came from Lisp, and in Lisp it was more the emphasis on function composition than the purity. And then Haskell came along and kind of tries to redefine and put more emphasis on eliminating side effects. And that's how we get these 2 variants nowadays. Okay, so maybe we know more or less what's FP. What is direct style then? Martin actually gave quite a good definition on the Scala, which is our annual Scala conference in Warsaw. Feel invited if you would have time in April. So Martin defines direct style as the opposite of continuation passing style and using a control monad. So that's kind of a negative definition. So if we tried to say what it is, not say what it is not, I would say that direct style is where the results of any effectful computations are available directly, hence the name direct, right? Directly, so not trapped in a future promise IO or something like that. That also means that we avoid using continuations, right? Either as callbacks or as monadic wrappers. But as I said, we actually need these continuations. We need them for performance, right? That's the reason why all major programming ecosystems moved to using monadic wrappers to represent computations like futures in Java or promises in JavaScript and so on, is because of performance, right? Because we wanted to more efficiently use the resources of the operating system, right? So we still need those continuations. We still need this performance. And we can actually do it. Nowadays, this is often hidden either by improvements in the language, right? In Kotlin, for example, we've got coroutines. So what Kotlin does is it translates the whole program into continuation passing style, and that's how it avoids having explicit continuations in the code or having to use monads. We have virtual threads in Java, which hides the continuations in the runtime. So they are there. You just never directly manipulate them. And we also have like more niche usages such as abilities in Unison or EIO in Occam, which I think is doing a similar thing. So the continuations are there. They're just hidden now beneath a syntactical shell. But syntax matters a lot because that's how we express programs. Okay, so how function is direct style, right? Is direct style, then I guess we are now equipped to actually answer the question. First of all, Scala is functional by construction, right? It is a functional language. We have all those tools at our disposal, right? We have functions as first-class values, ADTs, high-order functions, all with a lightweight syntax. So in a way, we only need a way to avoid spoiling what we already have in Scala. And to kind of compare different approaches, I created a very subjective scorecard of how functional a given approach is. And Scala is uniquely equipped to actually study different approaches to writing programs because we have a couple of ecosystems in Scala. Some of them are purely functional. Some of them are use monads like futures, but they also allow, they are not pure, and some of them are like direct style. So you can actually, using the same base language, you can compare all three approaches. So in our scorecard, what we will take a look at is how well the language supports the given construct. So here for Scala, these are the first three, right? Everything is nicely functional. But then we also have some other categories which actually depend on the ecosystem that you use. So first we've got the purely functional variant of using, if you know Scala, it's using either Katz effect or Zio. So if you use these purely functional effect systems, you eliminate all side effects, or at least you are supposed to eliminate all side effects, because that's done only by discipline, right? When you write code, you are supposed to wrap any side affecting code inside an IO monad or a Zio monad or something like that. But the compiler won't shout at you if you forget to do that. So, sorry. So that's why you don't get top points when it comes to representing effects as values. And we can compare that to like the direct style approach. The language is still the same, but now we get like less points, for example, for effects as values. We still use eithers, which is kind of representing an error as a value, but otherwise all other effects are unconstrained. But all the other scores are quite high. And we can do the same exercise for other languages as well. Of course, again, you might disagree on the specific points, but I guess, we get something like that, where Haskell, of course, is close to being perfect when it comes to functionality, but Scala in both variants is not far behind. So yes, I guess you can tell that direct style is a functional approach because you can actually use all of these techniques that I talked about quite extensively. I think also what's worth noting is that there are some attempts to do direct style when using the purely functional variant of Scala, but they're all limited, right? So it seems like it's not a concrete, it's not a rigorous proof, but it seems that direct style and pure function programming are at odds, at least when it comes to Scala. Like maybe you could do it, but it would be a different language. So all of these attempts to do direct style when using purely functional effect systems, the way they work is that they take a block of code and they transform it to continuation passing style. However, you can only use a limited subset of the language within the transformation, so you don't get to use the entirety of Scala. Most notably, higher order functions are problematic, which is, I guess, might be quite a limitation. Okay, so as I said, I wouldn't want only to stop like saying if direct style Scala is functional or not. I would also like to take a look at the practical perspective, right? The purely functional effect systems actually give us a lot of functionality that we might want to replicate in direct style. For example, if you're using purely functional effect systems, you get things like safe resource management, like safe refactoring because of referential transparency, like high-level concurrency streaming. You also get some bad sides, like a higher syntax overhead because you have to use the monadic syntax everywhere, the virality of the data types because you end up with IOs everywhere, the learning curve is a bit higher, and so on. So maybe we can eliminate it. So yeah, so the question is, can we actually use the function programming in the casual variant, and can we leverage for example, what's in Java to hide the continuations for us? what Java gives us with virtual threads, but keep some of the benefits of the purely functional effect systems and avoid some of the problems. And to do that, we built a proof of concept library called OX. It's open source. We had a 1.0 release a month ago or 2 months ago. And it tries to implement all the functionalities that purely functional effect systems give us, but in direct style. So a couple of examples. So here we have a high-level concurrency operator. So power will run these two computations in parallel. These computations are passed by name, and it will only terminate when both are completed or when either of them ends with an error. In a similar way, we have high-level operations for racing, timeouts, and so on. We also have a lower-level concurrency API, which is based on structured concurrency. So here you have a supervised block which delimits the lifetime of the threads created within. So it's guaranteed that when the block ends, any forks that you have created will end. If the block ends, but there are some forks running, they will be interrupted and will wait until they end. So structured concurrency means that the lifetime of the threads the limit is given by the syntactical structure of the code. So for resource handling, we have some utilities like a use function which automatically loses the resource, but it's not as safe as in the functional systems because you can still use resources such as a writer here in an unsafe way. So it still relies on discipline, right? It's not a separate type that the compiler will tell you you have to use the safe variant to actually manage the life cycle. So if you use it with the discipline, it will work fine, but you can still use it incorrectly and it will compile just fine. So then we have some APIs to replicate a functionality of functional streaming transformations. So if you know libraries such as FS2 or akka streams, so that's the same, but written in the spirit of direct style and with blocking operations in mind. So that's like a streaming transformation. It integrates with some other I/O systems as well. And finally, for the error model, ideally we would want to have an error model with 3 properties. So we would want to have different constructs for recoverable errors and for programming bugs. So something like panics and result in Rust. We would want to have an indication at call site that an error might occur, and we would want to be able to represent the recoverable errors as part of the type. And one solution here is to use exceptions for the programming bugs because they like silently propagate. And for the recoverable errors, we might use eithers, which meet most of these points. So you might say that using an either is again going back to using a monad, but either is a very different monad from I/O because it's a simple data type which you can deconstruct, which you can inspect. So either is very transparent, right? As opposed to an I/O or a future, which is very opaque and which you cannot really dissect. So here we are also using Scala's boundary break so that you get the nice syntax without having to use maps and flat maps. And yes, you have the indications at the call site where errors might actually happen. Okay, so to conclude, 1 minute left, okay. I would say that yes, direct style is casually functional, and that although many people insist that functional programming is really about eliminating side effects, I would say that there's a lot of value in FP apart from eliminating side effects, and that we should focus on that part, especially when talking and when advertising functional programming as well, because that's often what buys you the most benefits. If you try to implement direct style, if you try to implement the benefits of purely functional effect systems in direct style, you actually get a lot of these good points that so you can actually keep a lot of the benefits like streaming API, structured concurrency. You get a lower learning curve. you don't get the virality, but also there are, of course, some trade-offs. So, yeah, just 10 seconds. Okay. So yeah, you lose some things such as you don't have you don't have reversion transparency, or you don't get the safe resource usage. So my last slide, just a couple of links. It's all on the website. And okay, thank you. And sorry if I overrun.
For Scala F can set up already. Okay. So questions.
Hi, thanks for the talk. I've got one question since the talk a bit about that analysis what functional style is. Did you think about, I understood that the scorecard you presented was done by hand. Did you think about formal approaches or sort of some sort of syntactic analysis or something to giving such a scorecard? Or was it not done manually?
So like a more rigorous approach to the scorecard. Well, it would be perfect to do it, but I'm not sure how you can do it objectively, so I don't have any good ideas on how on that. If you do, we can talk later. I would be happy to do it in a more like formalized way. Yeah.
Cool. Yeah, no, that's fair. Thanks.
Okay, thanks. Any further questions? Yeah.
How does a direct style functional programming work when you have like multiple effects? Like I know for the pure functional programming, when you have an either inside a future, inside another either or something like that, it becomes very complicated to make sure it lines up. What does it look like when you don't have all these like wrappers? Can you still have like error handling inside async, inside something else? And
I guess you don't have any problems with async because you just represent it directly, right? So you do side effecting. So the async is not visible in the type, so it doesn't complicate your types. So you would of course want to limit what you represent in types. I think errors are common enough that you do want to represent them in types. For the other effects, I don't know, maybe capabilities, but currently they are not represented in any way in type. Which is a downside, of course, but it's again the trade-off.
Okay, final question.
Hi, talk. I have a question. So, suppose I have existing Scala code base. It's very purely functional with cats or Zio. Is it possible to slowly introduce direct style into the code base? I guess my question is, can the two work together?
Yes, they can mix both ways. So you can run cats or Zio code in a blocking way, just an operation run sync, and you can use the blocking operator to construct an IO value which has blocking operations inside. So it's trivial to go both ways. And actually, since you asked the question, I forgot to mention Gears. Gears is also a library that Nguyen is working on, which is very similar to Ox. Sorry about that, just because of the time constraint. But be sure to check it out. I think it's in the links as well.
My Maui, how could you? Okay, thank you very much.
Okay,
it was a great
thank you.
And now for the next talk, we are going to learn about functional refactoring in Scala F.
Hello everyone, it is great to be following Adam's talk because he explained very beautifully about how important functional programming is for when we're using Scala, all the advantages. So I would be continuing to that as well. So I am Shrika, and our work I'm presenting on behalf of Shiv, Himanshu, and my mentor, Manasa. So when Scala reads like Java, so let's start with something familiar. In large code bases, we have often seen that the Scala code is more of imperative, and it has a lot of loops, mutable variables, nested conditions, and it works, but it's not in the Scala's strength. It can do much more. So we are developing a tool which would help us not lose the functional benefits of our code and provide the refactorings. So if we lose the functional benefits, then the code becomes more stateful and error prone, and it is very lengthy, and there is no structure in the code, and it is not safe for parallelization. When we do some refactorings to make it more functional, we can use parallelization benefit as well. So that's what we are trying to do. We created those patterns and suggesting the functional refactoring for the same. Let's look at an example. If we suppose have a sequential code which is doing a lot of computation, if we use a dot par, then it would parallelly do it, and it would be faster. So these kinds of transformations is what we are providing. In this code, we can see that there is mutation, use of conditions inside for loop, and our tool identifies it and just converts into parallelly using a map. And it is now immutable. So that kind of refactorings is what we propose. So let's look at a demo and see how this actually comes into action. Let me play the video.
I'm Shiv, and I'm going to give you the demo of Scala F, the functional refactoring tool. So this is the UX of the extension. You can see the refresh button, and once you click it, you get all the refactorings of this file. So here you can scroll between all the refactorings, and you can see that there are total 475 refactorings. Among them, 347 are loop refactorings and 171 are conditional refactorings. And if you click on the header of each box, you will go to the selected region in the code, in the text editor. And you can also see there is, when you hover over it, you can see the view details and apply refactorings. And if you have an option to edit your suggested refactoring, and you can either accept or reject it. So here I'm accepting it. There is also an option to, every time you save your code, it automatically fetches the new refactorings for the diff of the file. So you can see this refactoring is considered now. And if you toggle between files, it will also fetch the refactorings of the new file almost instantaneously. Yeah, so there are total 3 refactorings in this page. If you want to clear the UI, you have an option to clear, so it will clean all the UI, and you can also refresh the UI to get the UI back again. There's an option to scan the entire directory to see all the possible refactorings for all the files. Now it is processing all the files of the workspace. Once it's done processing, it will give you the summary of all the refactorings in the workspace. As you can see, in this workspace, there are total 43 files where there are refactorings found, and total refactorings are 627. There's also an option to add your custom refactorings to the already existing tool. So if I do the new pattern refactor, I have to give a new pattern.txt. Here in this txt, the custom refactoring patterns have to give in a particular format. So you have to give the pattern name, and you have to give the original pattern, and then the refracted pattern and the description of the pattern. When you give this, from the next time when you try to refresh the page, it will identify even these patterns. That is all from me. Hope you are excited to use this tool. Thank you.
There is a QR, you can scan it and use this tool in action. And the source code is available, and the code, basically the backend code, if you don't want to use the tool and just pass in your code base directly, you can do that too. It's easier for large code bases. When we talk about evaluation, so we tried to work through conditionals and loops, and it performs very well in large code bases also, and the backend is working great over there. So we can add more extensible patterns as well and use it in live development. Next, we would want to include it in IntelliJ and add more functionalities to it and test it for more use cases like larger code bases. And that's it.
Thank you very much, and thank you for saving us time, because we're a bit behind in the schedule and quite a bit of time left. Thank you. Okay, cool. Are there any questions? Yeah.
Thanks for the talk. Could you talk a little bit more about the language in which you define the patterns, and also how is it related, if at all, to structural search and replace, which, for example, IntelliJ IDEA has, where you essentially could specify a pattern of some sort of an AST of code, and then it would find those AST nodes and replace them with something else.
Yeah, so basically we go into the AST level and do that, and the backend code is also written in Scala, Meta, and quasi-codes. So we are doing it pure Scala-based, and it is not just search and replace. We are going through what it actually is in the AST and identifying how they are structured as well. Like if there is a for loop inside a for loop and things like that, then it gives better refactorings, and that's how it is. Thank you.
Thank you for the talk. The demo looks interesting. I have a question, because in the demo you showed that there's a template file that allows you to specify the rules. So is there any kind of verification about the correctness of those or those rules? What if I made a mistake in those rules?
Yeah, so it is basically the human-based, like we showed that in the tool we can check if there is an edit option. So it is based on human to verify the correctness of it, and later we might want to do it automatically, but right now it's done manually.
All right, thank you so much for your talk. I hate to have to ask this question, but I'm curious if you've benchmarked this against neural LLM-based approaches.
No, we haven't tried that. It's a good thing. We'll try to do it and get back to you. Thank you for the question.
Okay, thank you very much. Let's thank her again.
Okay, thank you so much.
And now, Finn is going to talk about debugging in the context of DSLs.
That's just my desktop background. It shows me that if I hit mirror right now, we should be good. Great. Okay, and let me just double check that. Come on. My VS Code is also openable. Okay. Okay, all right. Sorry for the delay there. Just had to deal with the inevitable setup thing. All right, so, hi. I'm here to tell you about my adventure trying to debug control flow DSLs. And I guess, as a preface, I should explain that when I say control flow DSL, what I mean is all those fun, monadic, applicative, like anything that basically takes your non-direct style code, turns it into an object, and runs it however slightly later than where you actually wrote your code. That's what I'm talking about here. And I realize now I should have just said indirect style, but hey, I wrote that proposal several months ago now. Anyway, as we basically all know at this point, the other presenters did a great job of explaining it. DSL development is really interesting in Scala. You can do a lot of really weird things. You got flexible syntax. You can query context, ask the compiler all sorts of really interesting questions that most languages wouldn't even let you try. And also you have a fully working JVM to do whatever you need to do. As a result, I, like many people, decided to build a DSL. This was kind of my ongoing motivation. The DSL is called Forger, and I will not particularly explain what it is. It's for term manipulation. It's a personal project. What's important is that I used it to write quite a lot of code that used this non-direct style DSL to do a lot of tree manipulations. And after a certain point, I realized I had done something wrong. There was something incorrect. The trees were coming out mangled. What do? I need to debug this. Oh no. And essentially, if you haven't seen this happen, if you try to actually breakpoint or get a stack trace into a non-direct style application, it's disturbingly short, has about 2 lines at the top showing like some random out-of-context call stack from where you crashed or breakpointed, has a bunch of random stuff from the DSL implementer. Even if it's you, it's still confusing, but the DSL implementer does not want you to think about these lines of code. You should not need to understand them, and it's hard anyway. And then towards the bottom, you get, oh, by the way, launch DSL, and then whatever scaffolding you had around that. And just as a quick note, like I said, I will not be elaborating on the Forger thing. I re-implemented all of this using the tail call standard library module just to keep it simple and accessible. So I will be using tail calls for the entire rest of this presentation. So essentially, in summary, that's not my code. I know my recursion is way more complicated and interesting than that, and I have no idea what this means. Indirect style DSLs basically all have this problem, where you will be just completely subverting the normal JVM call stack, and that's great because you might want to have your own mechanism to do all sorts of interesting stuff with threading, with choices, with backtracking and whatever, and maybe you just don't want your thing to Stack Overflow. But the downside is that you've replaced your entire natural call stack and none of your debug tools work anymore. That's unfortunate and it makes me sad. What I'd actually like to see when my DSL crashes is something like this, which, most importantly, is all my code, so I should understand it, or at least try. We've got a clear path from start to wherever I am in some form, and ideally, if I were to see this in a debug interface, I'd be able to click on it and navigate around and, you know, do the normal investigation stuff that you would want to do. So what do we do when we don't have something and we want that thing? We invent it. So that's exactly what I tried to do. Now, let's see if this demo works at this screen resolution. Don't mind me for a second. Okay, I think that's about the min-max of size, and I'll just full screen this for good measure. So again, this is using tail calls. It's that one little standard library thing to do tail
at runtime. It's not very interesting. It's a monad, and I made a function fn1 that does some not very interesting recursion based on a number n. It has this interesting little edge case at 42, which calls fn2. And if you go here, I've simulated a bug with the triple question mark. That's all this program is. You don't need to understand any more than that. So first, I'm going to show you the problem scenario. I'm just going to comment out this part. Sorry, comment out and save, not select all. And then I'm going to run it. And we can see our little call stack here, which is the triple question mark, some lambda that I do know, straight into tail calls, everything else missing. So what we want to see is, based on 50 to 42 recursion, we don't want to see a quite deep call stack, which may not be that interesting, but we want to see every step of it. And realize this is an example for a much more complex real-world case where the rest of the call stack is very diverse and goes through a bunch of crazy stuff. So let's run this again. And now it is waiting for me to trigger the debug mode and go. And now you can see an exception has occurred here. That would happen anyway. But what you can also see is a complete call stack that's been reconstructed. And you can see the value of n changing around. You can see you have all these records. You can see the source location info, and you can see that it starts at 50. That's basically all I have to show you about this. The actual demo, which again is just a prototype project I whipped up quickly, it does actually support breakpoints and single stepping and some fun stuff like that. But for the sake of time, I will just leave it here and get back to my slides. Speaking of my slides. Okay, and let's skip my backup for if the demo failed catastrophically. What just happened? What did I actually just do? The rest of this presentation will just be me explaining what it is, what does this prototype entail, then some philosophy and open questions about where to from here, and that will be it, basically. So, there's 3 parts here. You've got the usage sites of the DSL. We have to get the line number and file information from there. We don't want to change it, much at least. We have the implementation of the DSL, where we want to interfere with it and understand its notion of progress and points of interest. We have a debug adapter protocol implementation. And if you're wondering what that is, that's a semi-standard protocol that you can basically implement and talk to your IDE with, and it will just believe whatever you say and display it like a debug interface, which is great because that's what I wanted to do. All of this together gives you an IDE experience that looks suspiciously realistic and helpful. So, point 1, how do you gather debug info? Well, the simple answer is just use source code. Shout out Haoyi, it's great. Basically, that's it. But there are a couple of interesting things that come up. Turns out, actually, the first kind of nitpick that I ran into was I need to capture the value of a local variable. And I only discovered when I re-implemented this outside of my existing project, because in my big Forger thing, I could print the entire tree state, and that was great for debugging. But it turns out tail calls is so much simpler that you need native local variables to make sense of what's happening. So I just quickly shoved in a manual capture of the value of n and didn't worry about it too much. I think this is an interesting open problem, and I'll get into it. But yeah, the other thing that I have to point out about capturing debug info is that when you have higher order operators, you know, those functions that take DSL terms and then do something to them and output like a bigger term, that basically acts in the same way that debug info has to deal with macro expansion, and you end up with this sort of expand stack thing. And as a result, your debug info actually kind of has a stack form in the general case, and you can do some weird context metaprogramming to try and gather that. I will not elaborate on this, but ask me if you think that's interesting. The next point, like much more core to this idea, is how do you instrument the DSL? And on the right here, I have the entire relevant source code of tail calls. It's just one tail recursive loop. And it makes a bunch of matches and does a bunch of decisions. And essentially what I need to do here is mark with a little method call saying, hey, here I saw this debug info and this type of event occurred. That's it. Just put that in there, and that's all you really need to do to your DSL implementation. There's one interesting thing, which again only came up when I had to re-implement this for tail calls, which is, it turns out tail calls rewrites its own object at runtime, so I had to pass around debug info correctly on those rewrites, plus 3 lines of code. Not that big of a deal, but that was interesting. Again, Forge's architecture didn't require that, and that was an interesting difference. Last technical point. Yes, you really can just implement a full debug adapter protocol server in process, just sitting there watching your DSL run. It turns out that Eclipse has a library to do this, and despite the fact I didn't originally know this and wrote the entire Forger implementation using only sockets and UJSON. So, whoops, but it really isn't that bad. Took me 380 lines of code basically, and this goes from implementing what gets called when you call that point of interest method, to all of the semantics, most of which is optional. If you don't want to do it, just don't tell the editor and it will just not ask. And the most interesting thing really is, you know, people say, oh, it's not like the modern practice to use those Java monitor methods with synchronize and wait and notify and stuff. But here we're genuinely just passing back and forth between 2 threads that are genuinely supposed to block each other. So it turns out careful use of object.wait and you will get extremely far, and the whole thing just works. So that's basically the technical insights of how I built this thing. Then the more philosophical questions. So I just made up a call stack out of thin air. What does that even mean? Well, one way of thinking about this is it doesn't entirely matter. The fact that you have a growing, evolving sequence of events that you can see and think about is already pretty good. If you squint a bit, you'll maybe not notice the fact that when you call and then return from a function, it counts as 2 events and the call stack gets deeper. You know, it's not entirely natural, but this approach, you don't need to understand your DSL at all, you just need to understand the notion of progress, and maybe you could log rotate your stack if it gets really long to avoid consuming all memory on your debug info. That's not the only thing I tried though. In Forger, since I was the implementer, I actually understood its internal structures a lot better and had a lot more time to think about them. So I could actually identify kind of when your call stack got truncated and evolved in various other ways, and I was able to provide a more custom experience. This, I think, is generally like the more ideal outcome you would want, but it is not easy and is different for every single DSL, though they may have their own little patterns here and there, like, you know, commonalities in how their flow works. For instance, if you were trying to do this for a green threads implementation like we were talking about just earlier, hey, the debugger has a threads section. You can just tell it to populate that with whatever info you have, and it will believe you, and as long as what you're telling it is helpful, that could be a really interesting way to instrument various kinds of non-direct threaded programs. Just thinking about one of the previous talks. But in any case, these are some interesting things to think about there. The last main thing is kind of, okay, so are we done with native debugging? No. It's really important. Most of our DSLs call random lambdas all the time, and we might want to see what that packet of bytecode is actually doing. So there's this kind of idea that I have about multiplexing the native debugger with this other information and trying to build a more coherent experience. No, I have not tried this at all, but I think it's an interesting idea, and when I was practicing this at our research lab, someone told me Racket's runtime has something relevant, which is interesting and possibly a point of inspiration. All that to say, I have this demo for the tail calls thing where I just copy-pasted part of the standard library and modified it. That's at that one GitHub link. I have this evolving Forger project which has been experimenting with other versions of this. But if you want the proper example of like all these features, look at tail calls. Forger actually doesn't support breakpoints. It could, I just didn't get around to it. There are also a bunch of open questions. How, if this generalizes to non-direct style DSLs. This feels like something that could kind of help the ecosystem. I'm not really sure how, but this presentation is to solicit thoughts on that. There's also this question of relationship to native debugging, which I think is interesting, and I'd also be curious what people's feedback is. As a complete aside, I must chill that I am soon going to be graduating, and if any of you know any sort of research type job opportunities, I'd be happy to hear about those. That said, this talk is mostly about these DSL things. Thank you, and let me know your thoughts.
Thank you, right on time. So, any questions? Yeah.
Did you maybe take a look at Zio's approach to reconstructing stack traces? Because I think they are doing something with implicits and capturing the stack trace through a macro on every Zio call.
Oh, interesting. I actually had not heard about that at all. I should look into it. I suspect this may only work for virtual stack traces that match the normal control flow. Like there are DSLs where they just mangle everything in a completely different order. But for conventional DSLs, that would be a great idea, and I should look into it. Thank you.
Any more questions? Okay, let's thank the speaker again. And now for the final talk of this session. Yao Yu, who works at LAMP, and he's one of the people behind Explicit Nulls, one of our big projects, is going to give us his experience reports porting the code of the standard library for Scala to Explicit Nulls.
Don't spoil the content. So, hi everyone. My name is Yao Yu Zhao. I'm a PhD student from the LAMP at EPFL. Today, I'm giving a talk about to discuss our journey migrating a large-scale Scala 3 project to Explicit Nulls, these new Scala 3 features. And during this talk, I will describe the task and explain the problem we encountered, and I will describe some details about the migration approaches we take, and explain how do we integrate LLM into our tools. We'll talk about some details, how do we design the prompts and our workflows. We talk about more about how do we do the review and validation about our migrations. Then we will talk about our migration results. Now, let's think about the situation. You are given a task. You need to migrate a large code base to the new Scala 3 features. And this is really a large project because it contains about 200,000 lines of Scala code. And if you just simply enable these features, you will get about more than 600 about the errors immediately. How are you going to start your migrations? The truth is, this is the task I was given a few months ago. And the project we want to migrate is the Scala 3 standard libraries. Before 3.8, we used the standard library from Scala 2. But unfortunately, we couldn't use any new features from Scala 3. So the standard library itself is unfrozen in 3.8. So this is a good opportunity for us to enable these new features. And you can check the new standard library in this link. And the new features we want to implement, we want to use is the Explicit Nulls. So before we talk into the details about the task, I will first give some quick overview about the Explicit Nulls. Explicit Nulls is a new feature for Scala 3. It modifies the Scala type systems, which makes the reference types or anything, a subtype of any ref, non-nullable, such that the null or the lower capital null is the value for null, and the null with the capital letter N is the type for null, and such that null type is not a subtype of string anymore. So when you're trying to assign the null value to a string, you will get errors with the Explicit Nulls. To represent something to be nullable, you need to use the union type, such that, for example, here the variable b has the type string or null, such that in this case, of course, calling the method of string on a nullable value is unsafe anymore, so it will give you errors when you're trying to call the trim from b, saying trim is not a member of string or null. In able to cast it, you can still cast a nullable values into a non-nullable values using the .nn. but it will still show null pointer exceptions if the variable is truly null during the runtimes. You can find more details in the documents of explicitNulls. Of course, these features will modify the type systems, will modify the type hierarchies. When you enable these features, your code will break. And we do care about the compatibility. So we already implemented several improvements in the compiler to help users to gradually migrating to these new features. We have the flow typing to check the nullability in the control flow. We introduced the flexible types, such that the types from the unsafe world, from, for example, Java, you can treat them as nullable and non-nullable at the same times. We also introduced the unsafe nulls, so this is a language import. So you can temporarily disable the explicit nulls in some scope of your code if this part of your code is extensively working with null values. You don't want to check the nullability through its type. Then the motivation is that why do we want to migrate standard libraries to explicit nulls? Well, the kind of limitation is that we would trust the type from the Scala code which is compiled without explicit nulls. If this is based on the assumption that most Scala developers don't use nulls that often, so it's probably safe to trust them. But if you have the type from Scala, which is say string, we will treat them as string in explicit nulls. Then this would introduce the problems, such that in the standard library, so we have the apply function for options. It takes a parameter of A. We will check if the parameter is null. In this case, we return none. If it's not, we will return a sum. But if we want to use this in the explicit nulls, if you want to transform allowable values into an options, for example, in this case, you want to transform allowable string into an option string, then it will fail. Because when you apply the option, the type parameter will be inferred as string. So you couldn't pass string or null to option in this case, which is pretty bad. So with explicit nulls, of course, we do have a right choice to give the true null safety for these signatures. You really want to change the signature of the apply such that it actually accepts A or null. Then in this case, you can actually pass in string or null to the option, and it will actually return the option string. Well, we talk about why do we want to do the migration, but what's the first thing you will encounter? You will have more than 500 of arrows initially. So the arrows look something like that. So it's basically if you are assigning null to some values which is not nullable, or you're passing a nullable values to something which shouldn't be nullable. And of course, this is just the initial arrows. During the migration process, if you're updating the types, you will get more arrows. And also because of dependency, you can also get some different arrows, such as you are selecting some members from nullable values, or you're violating some bound, etc. And during migration, you will also see some crazy code from a standard library. So I copied this line of code from standard library, which is the collision-proof hash map. I copied it exactly, so it will return a sum of null values, and it will also return null. So it is actually return the result type for this is sum or null. And this is, we know they are doing this for reasons, because you are using null to represent some unsuccessful operations. But this violating the lessons we teach the beginner of Scala, like you shouldn't pass null to a sum, and you shouldn't return null for option type. So to estimate how many trainings we need to do the migrations, we can first just search the literal string null in the library of all the Scala code. There will be about 1,600 places using null. So at least all of these places need to be updated. How do I say the difficulty of this project? Well, I wouldn't say it's a difficult task, because if you are experienced Scala developers, looking at the code, looking at the error message, looking at the comment, you know what's the correct way to fix them. But it is a tedious task, because as a human, you need to read all the code of the standard library, and you need to understand all the error messages at the same time, hundreds of error messages, and you are doing all the migration at the same time. It's a nightmare. If this was 2 years ago, I have no choice. I just manually do the fix. And this is what happened 2 years ago. when we enable XSpace and also for the Scala library itself. And I can tell you it's a difficult task. But now, after 2 years with the development of the new tools, is there better tools we can use? Why do I say this is a difficult task at the same time? Now we can consider concrete examples. Suppose in your code, originally you have a function which take a type A and you are returning a type B. Then by looking at the body of this function, if you are calling the method on the parameter directly, then the code is probably assuming this parameter to be non-nullable. So you should keep the original type. At the same time, if you code at the beginning, you are checking this thing to be non-nullable, using some assertion or throw exceptions, then it should probably also not change the type of parameters, even though it can be nullable at the beginning, but we should keep the original types to encourage people to passing a non-nullable values to these functions. By looking at the body of function, if your logic is depending on the nullability of the parameters and you are doing things differently depending on the nullabilities, and you are also returning now in some of the branches or in some cases, then, for example, in this case, you should updating the type for the parameter and the result type to the nullable types. Well, this sounds like a good guide to do all the migration, but we do always have some exception in the standard libraries. There will be some places you don't want to add or not. So for example, here, this is a conversion function we take from the standard library. It is an implicit conversion which from IRA to RSX, such that you can use all the array operations on the IRA. By looking at the body simply, it checks the arguments to be null or not, then it will return null if the argument is null. Well, according to the rules I said in the previous slides, I should probably change the argument type to nullable and the result type to be nullable. Is this a good choice? Well, what would happen if we passing a non-nullable value to this function? It will still return a nullable value. So if you want to do further operations on the result, you need to add .nn, even though you know it is not nullable. So of course, we need to do something to check that if you are passing a nullable values, you get a nullable values. Yeah, if you are passing a non-nullable values, you should get a non-nullable values. We can achieve that if we are able to use some match types or some inlining techniques. But we are also migrating the standard libraries. We have lots of constraints. We cannot just simply add a new definition to the standard library. So the final decision is that we keep the types as non-nullable to encourage people to not passing a nullable values to it. You should check the nullability before you use it. Another case we want to keep the original type is something like this. If you have a field which is initialized to some value and you working with it in some period, and after, for example, in this case, after evaluation, you assign it to null for garbage collections. Well, of course, you can say the underlying field should have the nullable options because you are assigning a null value to the field. But if we do that, you need to add a lot of .nn or to the code, and you're also flow typing sometimes may not work. So even though your code assuming a lot of places to be non-nullable, you are still you don't know, you are not able to check nullabilities in a lot of places. So in this case, probably it's better to keep these types non-nullable. All of the slides I'm saying is saying that this kind of migration we want to achieve is not simply to fixing all the errors. Is we want more deep semantic understandings. Because we are working with the standard libraries, we are also facing some constraints. We want to preserve the runtime behaviors. We want to make sure the binary compatibilities. We want to make sure the API we updated is matched with the semantic requirements we want, such that the simple tools like if you want to use Scala fix to just simply add .nn to every places you have nullable values is not good enough. We want a tool which can understand our code, which can understand the comments, can understand the error messages, and it can achieve the behavior we intended. So what tools do we have? Oh, okay. After 2 years, we have the large language models. It seems to be pretty good at this kind of techniques because the large language model can understand code. It can read your comments. It can do all the sorts of generations. It is trained to do specific programming tasks, and it also because when you communicate with the language model, you are communicating in human language. You can describe your requirements in human languages, and it can explain the changes in human languages. I wouldn't say the large language model is smart enough to replace all the people, all the programmers, but I think it's good enough to do this kind of jobs. So our initial migration approach is just like a simple Q&A style of large language model approaches. We collecting all the error messages, and we just ask large language to fix them directly. Like if I saw like these files contains errors, I just pasting all the errors into the large language model, and I passing the whole files to it and ask it to fix. Well, it's actually pretty good at the small files, and because it can understanding the error places, and it can modify multiple places cohesively. But it do fails at a large scale. If I have a file contains thousands of lines of code, if I pass all this to a large language model directly, it will doing something weird randomly. It can deleting the code randomly. It can modify the comments randomly. So eventually, we have an enhanced approach with the large language model, such as after we collecting all the error messages, we will first group the error messages together in, like, if this function contains 5 error messages, then it must be related together with the parameters. Then we will collecting the code around the error messages with some context at the beginning and at the end. Then we also design a more detailed template for the prompt to give the large language model a specific rules about how to fixing the code. And we get a lot of benefits. Rather than passing the whole files to the model, we can reduce the token usages. It has a better local correctness, and I can simply just passing hundreds of files processing at the same times. And here is like the prompt I designed for this kind of task. At the first, I will give a specific task, and I'm asking the model to fix the errors only related to explicit loss, and it should follow the following rules strictly. And then I will passing the error messages relating to each other, and then I will put the code together. Okay, it did a great job, and I think for this project, most of the changes is done using these approaches. But it also has some limitations. It sometimes can also, it may not find the best approach at the beginning, so we need multiple try at the end to find the best migration choice. I may sometimes need to step in to make the changes I want and to guide the large language model to do the migration in the remaining errors. So this is kind of changes it made at the end. So it is able to change the field to null and add the annotation we want to enforce flow typing. It is able to update the signatures. It's able to add .n at the places you are only able to check nullabilities through some other logic. It's able to update the result types as we want. It's pretty good. So at the end, the total change is about like 1,500 lines of code. Well, you are saying most of the changes is done by AI. How are you going to trust that? Should I trust human more? Well, of course, we have a lot of testing by the compilation tests and the community project tests. We are also using a hybrid approach to ask for review from both human and the large language model, because I will give a detailed document about how you should do the migrations. You should do this in this case, you should do this in this case, and we are collecting the review from both sides and do the final patches. And surprising is that even though we trust human more, there was a typo in the changes. We couldn't, after few rounds of human review, we couldn't catch that. And it's not catched by the testing as well. It only be caught by our, like the coding agent at some point. So I was just saying that the large language model can make mistakes and the human can also make mistakes. So this is my workflow in overall. We first collecting all the error messages. We run the script to invoke the model to apply the changes. And optionally, we will step in and make changes we want. And we recompile again until everything is compilable. Then we run all the tests and community projects. We do all the hybrid reviews from both human and large language models. there was something I want to do, but because of time constraint, I wasn't not able to do before I finished this project. Is that because the way we are doing is that we only it is mostly working with the same files, so it's not able to looking at the whole code base at the same times. We are also looking at the edits before the current files. It is also not able to do the SBT or metals, but I think it's probably doable. And I also wrote some prototypes, which is really simple if you are using some AI frameworks such as non-graph in Python. So as a result, we successfully migrate the standard library, I would say, such that we don't have any behavior changes. We make sure the binary is compatible with the previous standard library, such that if you are not using explicit nonce, using the new library shouldn't change anything. And we also sure everything pass our tests, all the commit builds looks good, and it will be ready for the next Scala version, which is 3.8. For the existing projects using explicit nonce, the only noticeable change is in pattern match with regular expressions, because we do update the types such that it will actually tell you the result should be a nullable string. And I'm proud to say that all the core components of the Scala 3 has been fully null checked, which including the compiler, the standard library, the Scala doc, and the presenting compilers, etc. You can actually try the new standard libraries with explicit nonce if you're using the Scala CLI, such as if you specify you are using the Lightning version of 3 and you enable this explicit null flex. And thanks everyone. Hopefully we can push this explicit nonce to the next level in the following year.
Thank you. That was a lot of work, I imagine. Do we have any questions?
Hello, thanks for the talk. So in the final PR, maybe you said this, but maybe I missed it. So was it just changing the signatures and ending .nn, or was there are some bug fixes that surfaced as well?
Sorry, can you
so in the PR, migrating the standard library to explicit nonce, was it all changing signatures, or did you fix some code in the process as well?
I think it is focused on changing the updating signatures. We don't change the code behaviors because.
But maybe you found some bugs in the process of updating and by running the compilers, maybe the compiler found some bugs really.
We didn't find any serious bugs. It's just like of course we need to updating the compiler as well because it has a better types when you comparing together with the standard libraries. We do need to insert .nn in some cases, such that, we have the flow typing. For example, if you compare a variable with null, then at the branch you can assume it to be non-nullable. However, if the nullability depends on some other logic, like if it depends on some numeric variables, then the flow typing won't work. So we have to insert .nn in this case because we assume it to be non-nullable at this point.
Okay. One more question.
Hi, thanks for the talk. So I was wondering if you have kind of like some estimation of timeline on like how much we spent on actually running the LLM or developing an approach to the thing and then doing comprehensive review. And do you think like in the end we save time?
Yeah, I do think it saves a lot of time for me. Like especially for the first step to do the migration. If I would do it manually, I have to look at all the error message, and if I change one places, there are larger error pop out at other places. It's just tedious. And if I use my tools, I can just do all the migration at the same times, and it will give a pretty good result at the beginning. Of course, I need some manual to review. Reviewing all the changes is much simpler than to actually writing all the changes.
Something a little bit detailed, like so. You did say that there are some places where changing the code to fix one thing will pop up errors in other places, right?
Yeah.
Is that something you kind of have to do in a loop with an LLM?
Yes.
Or
yes. For example, if if we figure out that the result type of a function should be nullable, then everything depending on this function needs to be updated eventually. It's something like that. So yeah, it is updating a loop. So it will first updating function, and in the next iteration, it will find new errors. Then we apply the tool again until everything is being fixed.
Thank you, and let's thank him again. So we'll have a 40-minute break and reconvene at 4 p.m.
Okay, hi. You can scan the QR code if you want to click on the links in the slides, otherwise it's not very useful. So my name is Matt Bovel. I'm a PhD student at EPFL, and I work between two labs. I work with Martin Odersky on the Scala compiler, and I work with Viktor Kunčák, who is making the stainless verifier that allows you to prove some properties on your Scala program. And basically, my job is to make a link between these two labs, and in particular to bring some of the verification features of stainless into the Scala compiler. So what I present today has been also done in collaboration with two students, Quentin Bernet and Valentin Schneeberger. So let me show you a motivational example first, so that you understand why I want to introduce these logically qualified types in Scala. So here you see a zip function. So the zip function takes two lists and creates a list of pairs where the first elements come from the first list and the second elements from the second list. So as you know, in the Scala standard library, if the two lists don't have the same size, the result is truncated to the shortest list. However, you might have made a mistake if you don't pass two lists that have the same size. So maybe you want to verify that. So how could you do it today? Well, you could use assertions. You could add a require, so that's basically an assert, but that checks a precondition of the function. You could require that the list of both sizes are the same, and at the end you could add the ensure, that's also just an assert for a postcondition, to document that the result has the same size as the inputs, okay? So that's nice. However, it comes with some limitations. First, that's a runtime check. So you pay for some overhead at runtime. Also, you have no static guarantee. So it's only checked for the inputs that you will actually pass to the function. You don't have any guarantee that that works for all inputs. So same problem as for unit tests, right? You just check some specific instances of your problem. It's not part of the API. As you can see, it's inside the function, so you don't see it in the documentation. And we will come back to that later, but it's a bit hard to compose. So we have a lot of support for types in Scala. You can pass type parameters around, for example. With assertions, you cannot make use of these features. Okay, so another possibility could be to use existing advanced Scala types. I will not spend too much time on that slide because I don't have time to introduce all these slides, but basically if you use path-dependent types, compile time operation, match types from Scala, you will also have some limitation. That works only to describe the fields of object. For example, it's limited to basic reasoning like constant folding and reasoning about constant, but you cannot encode much. Another problem is inference. These very advanced Scala types are hard to infer. And last but not the least, you have a completely different language now to talk about your assertions if you encode them at the type level. While with the nice assertions we had before, it's just terms, right? You just write that code like you would write any Scala code. So what could we do? Well, my proposition would be to introduce what we call logically qualified types. These types basically allow you to lift assertions at the type level. So here is again the signature of the zip function, this time with logically qualified types. You see that we require a list of B, and after you have this with, and then you have a condition. This condition is just a term, an expression that is of type Boolean, and that must be true when we call the function. Similarly, you see here the return type, that the result that we name L here has the same size as the input, okay? So I wrote that here. The return type means that any value L of type list AB here, such that the condition is true. So we define effectively subset of values of some type that fulfill a condition. So that's absolutely not new. It exists in many other languages. It dates from the 90s. The most known implementation is liquid types for Haskell. And we also had some previous work in Scala. So I will not have time also to go through all these different existing implementation, but maybe just one main difference with liquid Haskell that we have is that we want to treat these qualified types as first-class types. In liquid Haskell, it's a bit different. Actually, liquid Haskell is a plugin. It doesn't work in the main liquid Haskell compiler. And you write these refinement types as comments. So you see them in green here, okay? So you have like 2 layers of types, which is exactly what I would like to avoid in Scala. I would like to have a simple system where these types integrate and are written exactly like other Scala types. Okay, so let's just see the syntax a little bit in details because it might seem strange at first. But you see a qualified type start with curly braces, then you have the binder, which means for any value of that type. Here you have the parent type, and then you have the condition. Just to note that it should not be confused with the existing structural refinement types that we have in Scala and that we saw this morning, for example. So structural refinement types are a bit different. That's an existing feature in Scala that allows you to refine the type of a field. But these types, they also start with curly braces, but then you see a val or a def afterwards, while the logically qualified types start with a binder, then a parent type, and then an accession. We also have a shorthand syntax. So if we have this example of zip here, with the full syntax, the long form syntax, you would need to repeat the BS binder here inside the curly braces. However, we already have a binder, we already have a name for BS, so you can just omit the curly braces and the binder all together and just write the qualified type like that. So you can reuse the BS binder that already exists. Okay, so that was an example for zip. We could also define the type of concat that concatenates two lists together, for example. Here the result has the size of the sum of the size of the arguments. And what you can check today with my prototype, for example, is that if you concatenate two lists, x's and y's, and you also concatenate two lists, y's and x's, and you zip them, then that type checks because the system can derive that they have the same length because the length of x's plus the length of xy's is the same as the length of xy's plus the size of x's. If instead you try to concatenate two x's here, you will have a list of a different size than the first argument, and then you will get a compile time error. Okay, so just a note on what can you write as predicate, so what can appear there. We talked before a lot about functional programming, about properties of functional programs, and in particular, we want to work only with pure and immutable functions and data structures. So if, for example, you refer a var in your predicate, you might be in trouble later because, of course, x might change. So the fact that y has that type corresponds to this predicate is only true as long as x does not change. And that would be very hard to track, so for now we just forbid it. You cannot refer to mutable variables from a predicate. Something else may be a bit less obvious that must be forbidden for soundness is equality on classes that are not case classes, because as you know in Scala, normal classes have reference equality. So actually here you create two different instances of the box class, here on the right-hand side and here in the predicate, and these two would not be equal from the equal method, right? So that we also forbid. So if I have to summarize it, currently the predicate language is restricted to fragment of Scala consisting of constant, stable identifiers, field selection over val fields only, pure term application, type application, and constructor of case classes without initializer. And where you don't override the equal method, of course. Currently, we are actually not checking that functions are pure. That would be an extension of the system. And we are also not sure that would be a good idea in general, because it would require a lot more effort from the developer to prove that all their functions are indeed pure. But that might be future work. Now you might ask, okay, nice, we have these types, but how do we actually get an expression of that type? Because as you know, in Scala, the type, for example, of x plus 1 is just an int. And we don't want to change that. We don't want from one day to the other to say now, every time you use plus in your Scala program, it will get a very precise type that is a qualified type. No. For backward compatibility, it's absolutely not an option. Also for performance, it's not an option. We don't want these big types everywhere. Instead, we want to introduce them only when they are expected, because we always know what the expected type is in Scala. So if you do write an explicit type annotation, like here, then the system is able to derive that indeed you have an int that is not only an int, but that is equal to x plus 1. This simple process has a name, it's called selfification, but that essentially just means that if you have an expression E, you can give it the qualified type x equal E, okay? We can also do that if you have function in your expression. That's something that would not have been possible with the existing things in Scala, for example. Sometimes you still don't know exactly what the value is. Let's say I'm reading something from user input, for example. There is no way I can give it a precise type directly. So what can I do? I can do a runtime check. How do we do runtime check in Scala? Well, we have pattern matching. So let's say I'm reading an ID and I want to make sure that it matches a specific regular expression. So here it's a regular expression that defines what the valid ID is. Well, I can just define a type alias ID here. So it's all strings that match this regex. And then I'm able to match on that type, and that will effectively insert a runtime check, checking that my value matches this regex. And when I'm in that branch, ID has the type ID, so I'm sure it matches ID regex, okay? Sometimes we want to just fail if the test does not work, so you have a shorthand for that. It's called .runtime checked. You can write it like that. And that just desugars to a check where we cast if the predicate is indeed true, and otherwise we throw an illegal argument exception. Okay, and of course, as with any other Scala type, you can also do just full unsafe checked with as instance. Often these are not checked at all, but that would not be the goal to use that, of course. Just a note, as you know in Scala, type parameters are erased, so we don't have access to them at runtime. So in the case of a list, for example, you cannot match a list of something, whereas it's a qualified type or not, that in general in Scala. What you can do, however, quite easily is to use the collect method, for example, and that would convert my list of int to a list. So basically it filters the element, and then it ensures that the resulting elements indeed have the type pos, right? So it filters and map at the same time, if you want. We could also define a shorthand for that, but I don't know if that would be useful. Okay, just then a note, well, more than a note, but a few explanations about how subtyping works for these qualified types. How do I know that a qualified type is a subtype of another? Well, there are two things to check. First, if I have this qualified type here where the parent type is T, and this one where the parent type is S, I need to check that the parent types are subtype of each others. And then what do I need to do for the predicates that are attached to each of these types? Well, I need to check that for any value, if the predicate of the first qualified type is true, then the predicate of the second qualified type is also true. So we need a solver that is able to check logical implications. And that's exactly what SMT solvers that we saw in the previous talk do. In this prototype, we're not using an SMT solver. We just implemented a simpler more lightweight solver that is based on a few things that I will describe quickly, but basically constant folding, normalization, unfolding, and equality reasoning. So constant folding, I think it should be pretty clear what it does. It will reduce operations on constants so that you know that 1 plus 1 is equivalent to 2, for example. Normalization enables you to reason about algebraic properties of operations, for example, on integers, so that you know x plus 1 is the same as 1 plus x. That's what we needed for the example zipping to list, for example, where the size were both symbolic, but we needed to reason about commutativity of addition. And we have other normalizations as well. We have something else, unfolding of local value definitions. And I think that's very important. I said before that it's hard to do inference well for that kind of advanced types. And we don't want to type everything with very precise types. So that enables you to have here a y that is just an int. It doesn't have a precise type. But if you use it in a subtype check, the solver will be actually able to see the definition because it's a local val and to unfold it. So it will derive that y and x plus 1 are actually the same thing. And I think this is crucial so that you don't need to write these explicit types everywhere, but instead they can be recovered from the definitions. We also have some kind of equality reasoning. So if something is equal to something and that thing is equal to something else, we know that the first and the last things are equal by transitivity of equality. We also have congruence of equality. That's some properties that we can check. We use a graph-like data structure to check that. Okay, so that's what the solver can do today. We also have some compatibility with other Scala types. So we have literal types in Scala. That's actually a type. And we can know that if we have a qualified type saying the value is equal to 3, that's actually the same. And we plan to support interaction with other Scala types in the future. Okay, so what is the future work? Well, it's to fix some bugs, of course. Then we want to make a pre-SIP. So a SIP is a Scala improvement proposal document to actually get the feature into Scala. So we will first do a pre-SIP to get feedback from the community and then hopefully make a SIP and standardize the feature. Okay, so I will not talk about the future work unless there are questions about that. I will skip to the conclusion slide. So I presented the syntax, how we can introduce these qualified types with selfification or runtime checks. I showed you a bit what subtyping we support today, and I told you about the future work that is the SIP. Okay, thank you very much, and if you have any questions.
Thank you, Mathieu, for your presentation. Any questions?
Thank you so much for the talk. We've been working on Liquid Java for a couple of years, so I'm really curious about some of your decisions and how could they integrate with our work so you could support at least some mutable stuff in your project. But I think right now you don't support uninterpreted functions or measures, as they're called in Liquid or logical qualified.
No measures, but uninterpreted function, yes. If you just call a function, it will be considered as an uninterpreted.
So how do you do the pattern matching there? Because you cannot runtime assert it.
So I think we can already do some things with pattern matching, but as soon as you have recursions, so we would need mergers there, and indeed there will be some more work to be done. Yeah.
Okay. I know I would be curious to talk to you about the later stuff that you skipped.
Yeah.
Any other question? Okay, so let's thank Mathieu again. And I'll ask Max to join us on stage. So Max from the University of Edinburgh will present to us how they built a type-safe compiler framework that is compatible with MLIR.
Hello, everyone. So, hello everyone. My name is Max Kret. I'm a second-year PhD student at the University of Edinburgh. And I'm here to present SCARE, our project in collaboration with Emilian Bauer there, and as well as both my supervisor Jackson Woodruff and Amir Shaika. Right. But before we start, let's set the scene sort of. So, in a while now, we have seen a rise in sort of heterogeneous hardware as to sort of get low-level optimizations, as well as DSLs to sort of get the high-level interface and more sort of abstraction-aware optimizations as well. And at the backbone of these inventions are compilers or compiler infrastructure. And we see that it's been sort of rising steadily for the last X years. And we argue that part of the reason for this is that there is a lot of code duplication for different compilers, especially at the middle end bit, where different compilers sort of, how do you say it, rewrite the same abstractions over and over, as well as transformations over them. And the current sort of state-of-art tool to manage this complexity that is very promising is MLIR. And it allows you to sort of combine all of the abstractions and transformations at that level, and allows each of these compilers to lower to MLIR and then sort of let MLIR take care of the rest. So, in short, MLIR achieved this through sort of a unified structure for different compiler abstractions, as well as the tooling. So this is done through three main things. Attributes, which is compiler metadata, or compile time values, or types, as well as operations, which are sort of like constructs of a language, or sort of abstract units of computation. And dialects, which package them into sort of namespaces. As well as the single static assignment representation, SSAIR representation. And tooling, which is sort of a C++ code base, different APIs, different DSLs like TableGen, and yeah. So let's see, for example, how a simple dialect would look like, for example, in MLIR. So here we have addition, a simple sort of a language with just addition and constants. So this would be an example program within that we could express in this language. It's addition of 17 and 42. And in MLIR, this would look sort of like this in the MLIR IR, where we sort of define the first two constants as operations, and then we add them. And here we can see this is an example of an attribute. So yeah, and this is an example of an operation, whole thing, and this sort of structure that you can see where we sort of define 1, 2, and then add them together and produce 3 is the SSA structure. So sort of static single assignment. Right, so that's great. One would think once you learn all these things, right, it would be easy to sort of get started with efficient compiler development. So yeah, let's go for an example of writing MLIR. Right, so on the left-hand side, we have sort of a high-level operation which defines an even integer constant that contains a compile time value, so a constant value, as well as produces a SSA result value. Right, and on the right-hand side, you can see the C++ code. So it's a bit of a mess. It's a bit hard to read, but the key point is that the way to do this, the way to express this in MLIR is through sort of generically typed lists that are then indexed through getters. So on the value integer, this is actually gotten for this get properties, which is a method that indexes into a sort of struct or a dictionary in C++, and then it's cast to an integer type, and the result is indexed over a generic list of values or attributes. And here you can see the casting back to its sort of original type. And how you may wonder how we actually verify the logic or the types of these things. Well, it's at runtime for this sort of verify function. Yes. So that's also a lot of boilerplate. Can we do better? And yes, we can. MLAR has this tool called TableGen, which is a sort of operation specification language, this DSL within the framework, that allows you to more sort of declaratively define operations. And here we can see that, that the value as well as its types and the result as well as its types is sort of contained within the sort of signature of this. And where's the logic that verifies the typing information? Well, it's auto-generated, sort of, yeah. So how about more complicated constraints in TableGen? They're written in C++, of course. So we actually haven't implemented our logic yet to verify that an operation is supposed to be even, right? Which is there. And since TableGen is sort of only a specification language, it actually does not have Turing-complete capabilities. So the way to do this is just write C++ code as text, which is then is then basically pasted into a C++ definition or generated C++ class for the operation. Yes. Okay, so that's interesting, but can we define rewrites over TableGen operations? So yes, we can, kind of. So TableGen supports pattern-based transformations, and these are sort of shown like this, where we have an addition of a constant and another constant, where we sort of merge those two constants together. And we can do this through defining our sort of matcher. So the thing you can see on the top on the left-hand side. And then defining what we produce based off of this, right? So it's kind of like pattern matching, but implemented in TableGen. And it is a graph pattern matching transformation infrastructure, so it's DAG to DAG. Yeah. So what about more complicated rewrites? They're also written in C++, of course, right? So this is an example of a transformation in MLAR codebase. I don't really know what it does, to be honest. But the important bit here is this part, which is actually a problem of the generically typed operations that they have. And it allows you to do things like this, where you sort of manually check the types of different components of operations. And crucially, we can see here at the very bottom, I don't know if I can show this, that once we're sort of done with checking, when we only have one option left, we sort of just cast it to the relevant type. And this is a maintenance problem, because if we actually go back and change our operation definition, this won't get flagged by the compiler, and it will fail sort of unexpectedly at some point. Right, so now we could see a more clear picture of the MLAR ecosystem, and it maintains a sort of steep learning curve, right? It features advanced concepts within it, like template metaprogramming, and sort of fragmented tooling, where you sort of, sometimes use TableGen for certain things, but then you actually need to fall back on C++ when you can't express them. So this brings me to goal for scare, right? And in short, we want to create a framework that has a sort of high-level native interface within Scala, but low-level performance of the sort of C++ code base of MLAR. Yes, so here's sort of a high-level framework diagram. written in Scala. So we essentially wrote the framework in Scala. It features a shared MLIR structure. So we use the same IR structure as MLIR, so with dialects, attributes, operations, etc. And it's completely standalone. So it's a complete re-implementation of MLIR in Scala. And these come with benefits such as the shared MLIR structure allows us to sort of trivially interoperate with MLIR itself, where we pass the IR through a textual format into MLIR. And its sort of standaloneness allows us to, and its high-level interface allows us to more easily sort of prototype new things and teach these sort of core compilation concepts to a wider community or to aspiring new compiler engineers. So how do we write operations in Scala? Where, well, there are just case classes, right? We include the name as well as the type value within the signature of operations, and where's the logic that verifies the typing constraints? Well, it's already contained within the type signature. So they're correct by definition, right? Like when we define them or we instantiate them, we already know that they're correct. So we don't need to do any casting as well. And what about transformations? It is also just Scala, right? So we have the same transformation as before, where we sort of merge the two constants here. And we just use simple Scala pattern matching, right? So we have case classes that automatically derive the necessary apply and nullify functions. So we get this kind of for free with sort of minor additions, such as the owner class, which is a simple extractor, as well as this pattern function, which is basically just takes in a partial function and allows us to sort of neatly replicate the API of TableGen, but natively and with little effort. So yeah, it's just basic pattern matching in Scala. Right, so sort of to summarize the differences and compare the TableGen and Scare. TableGen sort of, TableGen is a separate DSL. So it has a separate syntax to sort of C++, and also a separate compiler that needs to be maintained within the framework. It features untyped C++ code that gets pasted into the sort of generated class definition. You have this sort of fragmentation, right, where the operation you define in TableGen, but actually the actual class exists within C++, and you transform it sometimes in TableGen and sometimes in C++. And you have these sort of generically typed lists that you define getters over, and you need to re-verify your typing constraints at runtime. And to compare this with Scare, it is just Scala, right? Yeah, that's it. And with an added sort of, I guess, contribution or thingy where our types are contained within the signature. So our data structure for these operations is actually entirely different. Or, yeah, it's different from the one in MLIR. Where we sort of have this sort of specific interface, and then and in MLIR you have this generic interface and getters over it. So how do we do it? We use Scala's metaprogramming, right, to get this sort of zero-cost abstractions. And this is mainly through this, the core of this is this type class that we define, this companion type class, where the generic API that is otherwise present in MLIR operations, we include here. And it's necessary for context-agnostic transformations where we don't actually know the exact type of our operations, but we nonetheless need to access their components. We have a mutable unstructured class, which is sort of an escape hatch that allows us to sort of lower our typing constraints and sort of fall back on this MLIR-like generic class. And we have two methods, which is structure and destructure, that allows us to sort of switch between this well-typed and mutable untyped class. And here is a sort of worked way of how we would derive these things. Firstly, we take our operation definition, right? So our class definition, and we use a mirror to extract its metadata into like a class, right? Where we, as you can see, we sort of get the name of the value as well as its type, and the name of the result as well as its type. And then we use an expr, or a sort of AST representation of our almost runtime instance of the class, and we use the quotes library to then derive the specific implementations of these components. Right, so we see on the right-hand side this sort of generic list of properties, which actually takes the I and then it extracts the value out of it, as well as the results there, and yeah. And then we actually go back and we use a recent feature of sort of most recent Scala, or Scala 3.7 or 3.8, the deferred keyword, where sort of at compile time, we take this derived operation companion and replace our definition of this sort of generic API in operations with the derived the derived parts of the type class. Yes. So what's our progress so far? So here's sort of the summary of our qualitative measures, right? We, in a sense, were able to combine this sort of high-level API of table gen and sort of the benefits you get from a C++ definitions together into just Scala. As well as sort of even creating this new data structure for operations that allows us to express type constraints within the signature of classes, of operations, and for our runtime, we have two sort of benchmarks where the first one is where we sort of randomly generate operation constants and then randomly add them together, and then run a constant folding transformation over the sort of benchmark or the operations. And we see that we're pretty on par with MLIR. We're slower, but not significantly slower. And what's interesting is we've tested this with both the sort of Scala JVM as well as Scala native compiler. And at a certain point, we kind of see what we believe as benefits of JIT sort of kick in, where the JVM actually outperforms the Scala native given sort of enough operations. And then we have a second benchmark where we predictably generate the constants, where we have like sort of generate a constant, and then we add it, and then another constant, then we add it, and yeah. So here we can actually see the benefits of JIT, where the JVM actually manages to match the performance of low-level C++ MLIR at some point, right? It gets there, and looks like it might even surpass it. Well, yeah, the Scala native compiler sort of stays the same. So yeah, so takeaways. MLIR is a great tool. It allows you to sort of make use of sort of an extensive library of abstractions as well as transformations over them, and gets rid of the need to rewrite these in separate compilers over and over again. But it has a steep learning curve, and it could be very intimidating for people who want to just get started with the framework. We can use Scala to lower this curve without significant sacrifices in performance. And we're sort of opening the MLIR ecosystem to a wider JVM community, where we sort of can communicate with MLIR through this shared textual format, sort of very trivially, right, by emitting MLAR. And in the future, we want to push the performance of SCARE even further. So we've done kind of the naive and most basic things we could have, but there's still a lot of work to be done. We are looking for possible compiler use cases for our framework. And yeah, we, of course, welcome your help. We're quite new to the community, and we're really glad to be here. And thank you. Let's collaborate. Yeah. Thank you. Any questions?
Thank you, Max. Any questions?
Thank you. It was a great presentation. Thank you very much. The implementation specifically looks very cool. I'm a little bit worried about the because it looks like it's one order of magnitude slower, right? And that MLAR is already very slow.
Sorry, could you repeat the question?
Yeah. So the question is, okay, so basically it seems that your implementation is about one order of magnitude slower than MLAR. And MLAR, I think, is probably already pretty slow with all this object-oriented programming. So like in LLVM, for example, if a commit now that they're trying to improve the performance or actually not degrade it anymore, and so a commit that is like 3-4% slower doesn't get accepted. So what do you think about that?
Yeah, so you're right, but I think seeing these graphs makes us quite hopeful, because there is a lot that we still haven't done, and we have this sort of new data structure for operations that allows us to include the types within the signature, and there is a lot of work where we want to leverage this typing information at compile time, and then, for example, optimize our pass pipeline or like rewrites to sort of create a more optimized version of it. Because currently, it's sort of paying the cost of being generic, where it allows you to express pretty much anything, but yeah, it's hard to optimize it specifically. So yeah, what I'm getting at is the transformation pipeline is also quite generic, where you sort of have a list of transformations and then you sort of exhaustively apply them, and then you can do things manually to optimize it. But what we want to do is leverage the typing information and optimize the pass pipeline to make it faster. And then things like this, where we can leverage this type of information from the data structure to actually to make a more to specialize our verification, for example, at runtime, things like that. Just essentially include more typing information, more types everywhere, and yeah, hopefully it gets better. Cool. Thank you for the question.
Thank you, Max, for the presentation. Let's give him another round of applause. And now we welcome Yu Kong, who's going to tell us how we can build educational fragments for Scala.
Okay. Hi, I'm Yu Tong from Science Tokyo. I would like to share with you my ideas on creating an educational fragment of Scala. So the motivation of this work comes from an introductory functional programming course that I am teaching in my institution. The course teaches how to systematically design programs based on the Felice et al.'s program design recipe. And it is attended by second-year undergraduate students majoring in computer science. as a functional programming course, it covers topics such as algebraic data types, recursion, and higher order functions. So this course has long been taught using Scala because Scala is functional and it's close to Java, which is used in a later course taught in my department. I think Scala is a cool language, but after teaching this course for like 6 years, I realized that the full Scala language is probably not ideal for my course. And there are mainly 3 reasons. The first reason is that Scala often produces error messages that my students don't understand. So suppose a student wanted to compare a function argument with a number, but they used a single equal operator instead of the double equal operator. In this case, Scala will complain that reassignment to val is not possible, but this doesn't make a lot of sense to my students because they are not familiar with the notion of assignments. Yeah, and the second reason is that the semantics of some operations and the appearance of values can be confusing to novice programmers. For example, in Scala, we can concatenate a string with a number without converting the number into a string. And this kind of heterogeneous addition could be surprising to my students. And also, the resulting string is displayed without being surrounded by quotation marks. And that is inconsistent with my students' knowledge that strings are always surrounded by quotes. And the third reason is that Scala often exposes the what's happening? Okay, so Scala often exposes the object-oriented side of the language, even if we are programming in the functional fragment. For instance, higher order functions like map are a functional feature, but they use the object-oriented style dot notation. And this makes it a little bit challenging for me to explain, for instance, how many arguments the map function receives. So there are some inconveniences with full Scala. And in fact, these inconveniences are not unique to Scala. It has been claimed that no full-blown general-purpose programming language is particularly appropriate for introductory education. And this is why people have developed educational languages like Pirate and educational fragments of an existing language, such as the teaching languages in Dr. Racket. And inspired by these languages, I would like to create an educational fragment of Scala following these 3 design principles. First, the language has to have a restricted syntax, and it produces error messages based on that restricted syntax. And second, it evaluates and displays expressions in an easy-to-explain way. And third, it includes features from only one programming paradigm. Of course, there may be multiple versions of educational Scala suited for different kind of courses. And in the rest of this talk, I will sketch the design ideas for a version that will work well for my course, which is about functional programming and is attended by students with little or no programming knowledge. So let's start by looking at some of the constructs that I would include in my version of educational Scala. Variables are all immutable, and function definitions must have a body, and similarly, conditionals must have an else branch. For algebraic data types, I require all constructors to be fully applied because my students often forget to supply arguments. And for higher order functions, I would design their syntax so that they explicitly receive a list as an argument, just like in OCaml. And next, let's compare the error messages produced by full and educational Scala. So this is the same program that we saw before that performs comparison using a single equal operator. In full Scala, this is interpreted as an assignment, but in educational Scala, we don't have this notion of assignment, so we can guess the intention of the programmer and directly suggest the use of the double equal operator. And here's a different example. This function definition lacks an equal sign after the output type. In full Scala, this is interpreted as a declaration of an abstract method, but in educational Scala, there's no notion of method, and we require a function definition to always have a body, so we can again point out the error in a direct way. And here's another example. So we are defining a shape data type that has a square constructor taking in a length as an argument. And then we are creating an instance of a square, but we forgot to supply argument. In full Scala, this results in no error at all. But in educational Scala, we require every constructor to be fully applied, so we can remind the programmer to supply an argument. So these are some of my preliminary ideas for educational Scala, and there are many open questions that I would like to discuss with you. First, I believe that some of you have experience teaching Scala, and I would like to know what are some common challenges faced by Scala beginners. And I also believe that many of you are familiar with the implementation of Scala, and I would like to get some advice on how to implement such educational Scala. As I mentioned, there may be different versions of educational Scala, so it would be nice if we can make the language easy to customize by teachers, but I don't know how to do that. And although I'm proposing educational Scala for classroom use, it might be useful for like industry training as well. And in that case, would we design the language in a different way? And lastly, we might be able to address some of the beginner challenges without creating a new fragment, and I'm also open to that direction. So if you have any thoughts on these questions, or if you're interested in collaborating on this, please speak up or talk to me later. Thank you.
Thank you. So any questions?
Hello, thanks for the talk. I think one of the things that immediately popped into my mind is I think a lot of the examples that you demonstrated in the talk is something that I would call kind of like an actionable error message, right? Things like, so in your first example, we have this x equals 0, and the compiler was able to guess that maybe the intention was to do a comparison instead of an assignment. And this is kind of something that, for example, the Rust compiler is fairly known to have, that every kind of error messages that it produce has some kind of actionable thing. Like maybe you can try adding an ampersand, maybe you can try changing this, changing that. And I wonder if it's something that that you would want to have.
Okay. Thanks for the question. So yeah, my proposal is kind of like actionable error messages, but I'm borrowing the ideas from the teaching languages in Dr. Rocket. So they restrict the language to a beginner subset so that they can precisely report the errors. So maybe, so I don't know how Rust compiler works in terms of error messages, but yeah, probably we can just produce a bit better error messages without really creating a new restricted fragment. That's probably possible, yes.
Thank you.
Thank you for your talk. I know many people don't like AI, but I do think that you can make use of a LLM to generate more friendly, beginner-friendly error messages. Like the example, like you can provide and arrow, and maybe most of them generate good error messages. Thank
Yeah,
you.
thank you for the suggestion. Yeah, I think that's possible.
I was curious if you might, whether there is interest in examining the theoretical foundation of like how students pick up and then use the language incorrectly. So like psychological in the psychology sort of field to sort of mix it with the semantics of educational Scala. I'm not very familiar with this, so I was just curious. So if you treat it almost like a linguistics problem, you know.
Thank you for the idea. I haven't thought about like doing a theoretical like foundation for this project, but that might also help us design a good language. Yes.
Hi. This is not really a question, but a suggestion or an opinion as a student. I'm still an undergraduate, and similar to your students, I am learning Scala as a beginner. Although I've worked with FP before, so I do get the nuances that you have mentioned in the slide and why the Scala compiler behaves it does currently. And I would personally suggest not to fragment Scala to have an educational language. This might be a bit very controversial or very opinionated, because this encourages behavior from students to not go and learn the tool they're using and the semantics behind it. And yes, it would make it easier for students to rewrite their functions when it approaches errors. It does not teach them the underlying reason the compiler has those semantics in the first place. Perhaps you could see what Rust did a better example is the Rust book, which is called The Book, has an open source forked book by Brown University
Oh, yes.
called the Russ Lang.
Mhm.
And the person who actually created this book took inspiration from the philosophy behind HCI, human computer interaction,
Mhm.
and what is the general way users want to use a particular interface, the the standard library API, and how students would view it. Is they go through this in the book and quiz you and visualize it better to teach you things like ownership and borrow. Similarly, I would suggest, instead of creating a new fragment or a DSL on top of Scala or some other educational Scala special fragment of it, I would suggest a more concise book where you can probably go through the operations and types of Scala and quiz the students. That would teach them more about Scala tools than hiding than just forcing users to have extra compiler messages or error messages that tell you, oh, maybe you're missing something over here. For example, the assignment operation versus the equality check. That's more of a syntax error, and if students don't understand the reason behind the difference between the two syntaxes, use of equality, they will not be able to progress beyond the Scala development. They won't become language agnostic. They'll be stuck. They won't understand theory more than the language itself. So that's just my suggestion. Thank you.
Okay, thank you.
So I understand both points. So regarding your third question, I don't know if you know EDY, H-E-D-Y. It's a programming language where you can unlock new features.
Heidi.
Yeah.
Yes.
So that's an approach where you could add new language constructs to the parser, and it would enable new languages. I'm also not sure about the fragment, and I had a couple of other reasons. So I teach a similar course. We use Haskell. I'm not very fond of the laziness for that purpose, but if you open any Haskell function, second-year students can read them, right? So now, would your educational Scala functions be implemented in educational Scala itself or in regular Scala? Because it's useful for students to open the definition and be able to read them.
Yeah.
So that's a little bit tricky. Then things like losing the dot syntax for the methods, you lose the autocomplete, and by having the fragment, if they go into Stack Overflow or ChatGPT or whatever they use, they also lose this whole corpus because they're limited to a subset, which is what Hedy does on purpose. So I don't know what's the best trade-off, but I think these are all things to consider, I would say.
Thank you.
Thanks for the talk. So, are you planning to have documentation for the language? Are you planning to have some form of documentation for language? And also, would that be based on the sort of, would that be like a slice of the current Scala documentation?
I don't have a concrete idea, but I just want something that I can use in my class. Yes.
Thank you for the talk. I want to echo the other opinions to say you would have, we can have together much more impact to improve the error messages of Scala, of the Scala compiler in general than to define an educational fragment. On the other hand, it's much harder because by defining an educational fragment, I can rule out certain things like an abstract method, for instance. So, or I can say, well, I don't have assignments, so every equals must be a test, and the user forgot to write equals. But in a lot of these cases, I think the compiler can figure these things out. So, for instance, the val x equals 0, that should be possible, right? So if this is in a condition of an if, or somewhere where an expression is expected, rather than a statement, the compiler should figure out that probably that's what it's meant. It requires a lot of engineering. So I want to sort of have a call to action. I think this is very important, good error messages. We should put a lot of effort. It's not easy. You have to make put a lot of into it. But it's the question is, what can everyone do? We have tooling sprees and compiler sprees every 3 weeks. Mathieu is organizing them, so approach him. We essentially pair people with people who know the compiler, and so you can learn about the internals and work on that. If you feel that hacking a compiler is not your thing, then I believe it still would be super valuable to have a well thought out issue. So we have an issue tracker in Scala 3. To write an issue to say this is a confusing error message. I think under this and this condition, the compiler could give a much better error message. With that, other people can act on it. But I think a lot of value, what you did in your talk is essentially distill things to say, well, this is confusing. And once you, even if you say this is confusing, then this is already very good. If you say this is confusing because I believe that the compiler should be able to figure it out, that would be super valuable. So not just, so thanks for the talk, and everybody call to action. It would really help a lot if people would start doing that. Thank you.
Thank you.
So thank you for the talk. Let's give her another round of applause. Talk about her insights about mentoring the Google Summer of Code for the Scala.
Good evening, everyone.
Hello. You can start.
All right. Good evening, everyone. Kanupriya, I would like to, I'm hearing my voice. Just, my voice is repeating to me. Okay, it's still happening. All right, I'll start. So, good evening, everyone. I'm Kanupriya, and I would like to thank ICFP/'25 and Scala Workshop team for having me here today. I'm excited to share insights from my mentoring in the Scala system, lessons from Google Summer of Code. As Scala evolves, so must its community. Over the past year, I have mentored and helped organize a center's resource program, helping new contributors grow into confident open source developers, also using experience to get their first job in the industry. Drawing from real experiences, projects like Scala CLI, for us, I share what works and what doesn't. When mentoring newcomers in a functional, strongly built ecosystem. By the end, I hope you take practical lessons to make your own project more welcoming, sustainable, and community driven. A little about me. I have been part of the world for over a decade, starting my journey in data engineering in India and later moving to London to build backend systems at scratch. My turning point came when curiosity led me into open source, mentoring for people open source, and eventually co-founding LLM4S, a Scala first toolkit that connects AI with the Scala ecosystem. Today, I'm a global speaker and educator, creating hands-on courses to help developers grow. Over the years, I've worn many hats, from beginner to mentor, org admin to creator and builder, and every step of that journey has been powered by open. Scala has always attracted passionate engineers, but for newcomers, contributing to open can feel intimidating. The language's strong type system, functional style, and evolving tools make the learning curves. Yet Scala thrives on open collaboration, and its future depends on bringing in new contributors and maintainers. Over the past 2 years, as I served as board admin and mentor for Scala Center's program, helping early career development, building confidence, and making lasting contributions, I realized what makes Scala so special. As it's a very close knit community, it may be smaller than ecosystems like JavaScript, but that's its strength. Your work is noticed and valued. You get to learn by doing. And the best part, you can submit a PR and have it reviewed by the very people who helped shape the language itself. That's a rare and powerful community and opportunity that it brings. Mentorship is one of the most powerful ways to help people grow, and it gives newcomers real world guidance so they can learn faster and reach their potential sooner. In the Scala ecosystem, it's about sustaining the contributor pipeline. As the language evolves, we need new contributors to keep projects alive and thriving. Programs like GSOC are perfect for this. They give early career developers hands on experience with real Scala projects while connecting them with experienced mentors. But mentorship isn't one way, it's a two-way journey. As mentors, we develop empathy, leadership, and communication skills, and often rediscover our own excitement for the craft. Ultimately, mentorship helps us grow together and keeps the Scala community strong, inclusive, and future ready. Structuring is the key takeaway here. A well defined starting point helps contributors move confidently toward the ultimate goal without getting lost in ambiguity. The idea is to design your Scala project to be contributor friendly from day one. Clear documentation, simple setup, and logical project structure. Onboarding shouldn't feel like a maze. Choose the right first step, not the confusing one. Even small details like well written test suits or sample issues can act as powerful onboarding tools that turn new contributors into productive collaborators quickly. That's how the decision support will empower. Mentorship isn't just instructions, it's about making unfamiliar concepts approachable. In typed functional programming, the learning curve can be steep. The best way to help contributors grow is to let them explore and experiment rather than giving them all the answers. A contributor to contributor learning model, like pair programming, fosters collaboration and shared understanding, something I experienced firsthand at Sky in 2022. The key is balance. Guide when needed, but allow autonomy. Too much control stifles growth, too little leaves them lost. The sweet spot helps build confident, independent contributors, focusing on growth over speed. Contributors from underrepresented backgrounds often face hidden hurdles, not just in access, but in confidence. Imposter syndrome is real. As mentors, we must create a space where asking questions is seen as strength, not a weakness. Inclusion doesn't happen by accident, it needs structure. Time zones, language gaps, and communication norms should be intentionally addressed through async updates, clear documentation, and supportive feedback. When everyone feels valued and supported, retention rises and diversity becomes one of the project's greatest strengths. Purpose fuels persistence. The goal is to move contributors from simply completing issues to understanding their purpose within the bigger picture. Give them strength and freedom so they can choose their own problems which they want to solve, design their own solutions, and also take ownership of outcomes. That autonomy builds pride and accountability. Focus on progress over perfection. Celebrate small wins that have visible impact. That's what keep the energy alive. When engagement is nurtured like this, a short-term internship like a summer program transforms into a long-term collaboration because we all know we don't need any permission to keep working on open source projects. The impact of mentorship goes beyond individuals. It shapes the entire ecosystem. Lot of case studies and stories of an individual GSOC intern and their transformation after the program, absolutely electric, keeps coming. Through initiatives like GSOC, we have seen new maintainers emerge, projects become more accessible, and the infrastructure strengthen with better tooling and documentation. Most importantly, GSOC creates a sustainable future, setting clear expectations, developing leadership, and ensuring the community continues to evolve with fresh talent and shared purpose. So, these four students are an example of a successful case study from this year. They all are from different countries. Elven from Switzerland, Shubham and Anshuman from India, Gopi from US. Gopi is from second year in his masters, doing it from one of the universities in Texas. He has imposter syndrome initially during the process. He progressed a lot from not knowing what a PR is to actually creating and solving issues on his own. And towards the end of program, he actually was able to secure a research assistantship opportunity with the leading research professor at the University of Houston. All the other students as well are continuously working on LLM4S project despite the GSOC term ending way back and have all secured their next role after the summer internship program. I want to mention something that has been a big help, not just for the contributors who were able to secure their position in GSOC 2025 program, but all the other students who applied but were not able to get selected because we had limited positions. Rory and I created this program, LLM4S DevR, where we connect 9 a.m. London time every Sunday and we help resolve issues of anyone who is working on LLM4S project. So this is one way which I highly recommend to maintainers. So it's a global session where anyone can join. So we use it to mentor GSOC students. But apart from those, anyone else who is experienced can also join. Those who were not selected but yet want to learn, they can work with us. And it doesn't take too much time out of us as maintainers of the project. We all can join this session and see the progress of the project while learning from it. So, this is a very interesting take. Mentorship, how it helps mentors. So, there are some things that helps mentors. So, it's like reinforcement learning, breaking complex issues into simpler chunks sharpens clarity of thought and improves problem solving. Communicating those ideas, especially around functional programming, strengthens articulation and technical storytelling. Every mentoring experience teaches something new. It helps rediscover and shine concepts we often take for granted. And finally, exposure to different contributors brings diverse and versatile approaches, broadening how we think, lead, and solve problems. So, Google also organize a global event once every year. This is from 2024 and this one is from 2025, where as mentors we get opportunity to meet other mentors who are maintaining projects and we get to learn from them. Attending sessions like this helps us learn to make our organization better. Apart from that, it also helps us understand how underrepresented students, how people are managing different time zones, how there are people who get their first opportunities through a program like this but end up getting a real job at Google. So, this is a great way to actually meet fellow mentors. And now, ending this talk with a call to action. So, here is one of the chance to join in the Scala initiatives by scanning the QR code. Start with some initial basic issues to know the agenda of the project. Then, if you want to mentor and review PRs, you can go forward from there. But yes, LLM4S being the first Scala first AI toolkit, it has created a lot of new opportunities for all of us. And yes, if there are any questions and if you would like to connect with me, here's the QR code for that. And thank you for being a fantastic audience. And feel free to reach out and let's connect and work together to shape the future of Scala. And I apologize for some initial disruption with my talk. Yes. Thank you.
Behind schedule, so time for questions. Yeah, about if someone actually has a question.
Mm-hmm.
Okay, there is one question actually.
Hello, thanks for the talk.
Yes.
So, I was wondering, so, do you think that the like would the technical side be like the greatest barrier to contributing to Scala open source project? Like, I kind of want to have a grasp of like you know, some ordering of what is the hardest thing, and so yeah, it's kind of a hard to phrase question. So I guess you know what I mean.
Yeah, that's all right. I understand what you're asking. So good thing is, Scala open source, including this program, uh, everyone can participate in it. Like even if they are not technically good at Scala language. So we are collaborating as an organization with Rock the JVM, and Daniel from Rock the JVM creates very good Scala language courses. And anybody who's part of this program, we give them that entire course bundle for free. So that's some courses help for like learning Scala. But apart from that also, there is project specific learning that you get to do. For example, if you join LLM Forest Dev Hours and you are probably new to both Scala and AI, so as you start, you don't have to jump into learning all the concepts, but we help assign some beginner issues and also provide links related to that. So you can build as you go with us. So week by week, there is a structured learning route, but that's learning by doing. So you will only be given links related to the issue that probably you pick, or for as a beginner, your first few issues are picked up by a mentor. But let's say you're not a beginner, you are someone who is already working in AI space or Scala space and have a couple of years experience. So you can probably, and maybe you want to move into leadership roles, or want to see if you can be a technical lead at work. Probably you can join a project like this and try to mentor someone and learn from other mentors as well, like how they are doing, how it's an art, to give specific knowledge, to give your time in a very specific way, yeah, to other people, so even they can grow, and you can also balance your day job with open source work.
Thank you, Kanam,
Yeah.
for answering the question. So
Mhm.
first, before we close this, yeah, I mean, I think. Sorry. Thank you. If I didn't say thank you, but sorry.
Yeah.
I was gonna say, first, before closing today's, we still have 3 mugs. So if someone wants to get some, please do so. And we are obviously thinking of doing this workshop again next year, where we are welcoming obviously more submissions and hopefully more attendance. But even though if we're thinking about next year, we still have actually something planned. So tomorrow we have a joint session with Iwaku, the international workshop on aliasing capabilities and ownership, where we're going to have a keynote from Martin in the morning and 2 talks about capabilities, right? So hopefully we are looking forward to see you guys tomorrow. And to close today's, we have a photographer who is here to take a group picture. And yes, so thank you, everyone.
Thank you, everyone.